Hello there and welcome to Just About Earth, where curiosity gets cozy and the stories of our planet take the long scenic route toward rest. Tonight, we're going to drift back through deep time, far beyond calendars and clocks, into a world that once existed as a single quiet whole. Not a world of borders or oceans separating one place from another, but a world stitched together into one vast wandering land. Before we begin, let me ask you something gentle and simple. Where are you listening from right now? Is it late evening, early morning, or one of those quiet in-between hours when the world feels like it is holding its breath for just a moment longer? If you find this little journey soothing, or if it helps your thoughts slow down after a long day, you're always welcome to like the video or subscribe. It helps this small corner of calm reach others who might need a peaceful pause as well. Now, settle in, get comfortable, and let your mind loosen its grip on the busy parts of the day, because tonight we're going to follow the story of a planet that once carried all its continents as one, and how, over a stretch of time so long it barely fits inside human imagination, that single world slowly learned how to come apart. Long before maps had lines, long before oceans had names, and long before anything with eyes could look out over a horizon, Earth carried its land in a single sprawling shape. This enormous landmass is what we now call Pangea, though at the time, of course, there was no one around to name it, label it, or even notice it as anything special. It simply was. A vast stretch of rock, soil, forests, deserts, and shallow seas, all connected in one continuous sweep of land that wrapped around much of the planet like a great, uneven belt. If you could have stood somewhere near the centre of this ancient world, you could have walked for months, even years, without ever needing to cross an ocean. The idea of continents separated by thousands of kilometres of water simply did not exist yet. Instead, rivers flowed across enormous distances, carrying sediment from mountains in what is now Africa to lowlands that would one day become parts of North America. Winds crossed uninterrupted plains, shaping dunes and clouds without being broken by coastlines or open seas. At first glance, Pangea might sound like a kind of paradise for life. After all, everything was connected. There were no isolated islands, no distant lands cut off from one another. But connection comes with its own challenges. The sheer size of this supercontinent created extremes that shaped every living thing that tried to survive on it. Near the edges, where Pangea met the vast surrounding ocean, the climate was often mild and damp. Moist air from the sea could move inland, bringing rain to coastal forests and shallow wetlands. These areas supported rich ecosystems full of plants, insects and early animals that depended on steady water and moderate temperatures. Farther toward the centre, though, the story changed. The heart of Pangea was so distant from the ocean that rain rarely reached it. Winds lost their moisture long before they arrived, leaving behind enormous inland deserts. Temperatures swung wildly between hot days and cold nights. Life in these regions had to adapt to scarcity, learning how to survive with little water and few places to hide from the elements. Even in this ancient unified world, Earth was already teaching life an important lesson. Being connected did not mean being comfortable. It meant being exposed to a wide range of conditions, sometimes gentle, sometimes harsh, often unpredictable. At this point in the story, life on land was already well established. Forests of towering fern-like plants and early conifers spread across large regions. Insects buzzed and crawled through the undergrowth, some growing to sizes that might make you think twice before swatting them away. And across much of Pangea, reptiles and early dinosaurs were beginning to claim their place as some of the most successful land animals the planet had ever seen. These creatures lived in a world that to them felt solid and permanent. The ground beneath their feet did not hint at what was happening far below the surface, but deep within the planet, in the slow, restless movement of hot rock beneath the crust, a change was already beginning. Earth's surface is not a single unbroken shell. It is made of massive slabs of rock called tectonic plates, floating on a layer of softer, slowly moving material beneath. These plates move at about the speed your fingernails grow, which means that in the span of a human lifetime, they might shift only a few centimetres. But given millions of years, those small movements can rearrange the entire face of a planet. Pangea existed because these plates had come together. Continents that were once scattered had drifted inward, collided, and fused into one enormous mass. Mountain ranges rose where plates pushed against each other, and ancient seas closed as land closed in from both sides. But motion never truly stops. Even as Pangea sat there, seemingly stable, the heat inside Earth continued to circulate. Hot material rose from deep within the mantle, cooled as it spread outward beneath the crust, and then sank again, creating slow, powerful currents. These currents pushed and pulled at the plates above them, building stress in the rock like invisible hands gently but persistently trying to pry the world apart. At first, nothing on the surface would have seemed different. Forests grew, rivers flowed, animals migrated and hunted and nested as they always had. But far below, cracks were forming. In certain regions, the crust began to thin and stretch. Magma rose closer to the surface, weakening the rock from below. Over long stretches of time, shallow valleys appeared where the land was being pulled apart. These were the first quiet hints that Pangea's long reign as a single world was not going to last forever. From the perspective of a dinosaur or an early mammal, these changes would have been impossible to notice. A valley forming over 1 million years does not look like movement. It looks like a normal part of the landscape, but from our distant view, looking back across deep time, we can see those valleys as the first lines in a slow, planet-size separation. As the crust continued to stretch, something else happened. Magma broke through in long, narrow eruptions, spilling lava across the land in wide sheets. These volcanic events did not happen all at once, and they did not happen everywhere, but in the regions where Pangea was starting to split, they left behind thick layers of hardened rock. This volcanic activity had consequences for the air itself. Gases released from the eruptions drifted into the atmosphere, changing its composition. Carbon dioxide levels rose, trapping more heat and shifting global temperatures. Over time, this contributed to changes in climate that life had to respond to, even before the continents themselves had fully begun to drift apart. Plants that thrived in certain conditions started to struggle as temperatures and rainfall patterns shifted. Animals that depended on those plants had to move, adapt, or disappear. In this way, the breakup of Pangea began shaping life long before any ocean had formed between its pieces. One of the most important things about a single, massive landmass is how it controls the movement of water and air. When continents are connected, ocean currents are limited in where they can go. Winds tend to follow broad, sweeping paths across land without being redirected by coastlines and open seas. As cracks widened and shallow seas began to creep in, those patterns started to change. Water found new routes. Currents began to slip through gaps where solid ground had once been. Winds met new coastlines and rose upward, dropping rain in places that had been dry for millions of years. These shifts created new environments. Wetlands formed along emerging shores. Forests spread into areas that had once been too dry to support them. Meanwhile, other regions grew more arid as rain was diverted elsewhere. Life responded quickly, at least in evolutionary terms. Species that could take advantage of these new habitats expanded their range. Others found themselves increasingly confined to shrinking pockets of suitable land. One of the quiet but powerful effects of the breakup was isolation. When land is continuous, animals and plants can, in theory, move across it, spreading their genes and mixing with other populations. When that land breaks into pieces, populations become separated. At first, the separations were subtle. A shallow sea here, a widening valley there. But even small barriers can make a big difference over long periods. A river that grows wider, a strip of water that becomes too deep to cross, or a stretch of land that becomes too dry to survive can turn one population into two. Once separated, those groups begin to follow their own paths. Mutations that appear in one group do not spread to the other. Different climates and resources push each population to adapt in different ways. Over enough time, what began as one species can become two, each shaped by the unique conditions of its new home. This is one of the key ways the breakup of Pangea reshaped life on Earth. It did not just move land around, it rearranged the rules of who could meet whom, who could migrate where, and which traits were most useful for survival. Think of it as the planet slowly building walls, not out of stone, but out of water, distance, and climate. These walls were not meant to keep life in or out. They simply existed as a result of the land's movement, but their effect was profound. As the continents drifted farther apart, the world became a patchwork of separate evolutionary stages. In one region, certain plants might dominate, while in another, entirely different forms took over. Animals in one part of the world evolved features that would have made little sense in another. This is why, even today, the wildlife of Australia looks so different from that of Africa or South America. The roots of that difference trace back to these ancient separations, when pieces of Pangea began their long, slow journeys away from one another. Of course, all of this unfolded at a pace that makes human history look like a blink. The first significant cracks in Pangea appeared more than 200 million years ago. The full separation into the continents we recognise today took tens of millions of years more. During that time, entire groups of animals rose and fell. The age of the dinosaurs came and went. Early mammals, once small and hidden in the shadows, began to spread and diversify. Forests changed their composition again and again as climates shifted and continents moved. Through it all, the land kept drifting. If you could watch this process in fast forward, it would look like a slow-motion dance. Africa pulling away from South America, North America drifting toward Europe and then slowly backing away, India breaking free and racing northward to collide with Asia, lifting the Himalayas into the sky as it did. But from the point of view of a single living thing, nothing felt fast at all. Generation after generation was born, lived and died on landscapes that seemed solid and unchanging. The real motion was only visible when you stepped back far enough to see the whole story at once. There is something quietly humbling about that. Life adapted to a world that was always in motion, even when it could not sense the movement. The ground beneath every leaf, every claw, every bare foot was part of a slow planetary journey that would eventually reshape oceans, climates, and the very possibilities of survival. And in a way, that journey is still happening. The continents you know today are not fixed. They are still drifting, still responding to the heat and movement deep within Earth. The Atlantic Ocean is slowly widening. The Pacific is slowly shrinking. Africa is gradually splitting along a great rift that may, millions of years from now, become a new ocean. But those are stories that grow naturally out of what happened long ago, when the world was one, and then, little by little, learned how to become many. Long before the first hint of separation, before valleys began to stretch, and the crust learned how to thin and sigh under invisible pressure, the world sat in a kind of uneasy calm. Pangea, vast and uninterrupted, filled much of the planet's surface like a single slow-breathing organism. There were no great oceans dividing east from west, no familiar outlines of continents drifting across maps. Instead, there was land, and more land, and then even more land, spreading outward until it finally met the encircling sea. If you could drift above this ancient Earth and look down, you would not see the patchwork of blues and greens you recognise today. You would see a broad, uneven shape, fringed by shallow coastal waters and surrounded by a single immense ocean often called Panthalassa. That ocean wrapped around the supercontinent like a quiet, endless moat. its waves lapping against thousands of kilometres of shoreline that curved and folded back on itself in slow, gentle arcs. In this time, the planet had settled into a rhythm that felt, at least on the surface, steady and reliable. The land did not yet carry the deep scars of rifting, or the long, narrow seas that would later slice continents apart. Instead, mountain ranges rose where ancient collisions had pushed the crust upward, and wide, flat plains stretched out where erosion had slowly worn those heights down again. Rivers traced patient paths across the land, often travelling incredible distances before finally reaching the sea. The air above Pangea moved in sweeping patterns, unbroken by open oceans cutting the land into smaller pieces. Winds could cross thousands of kilometres of terrain, carrying heat and dust, moisture and cold, shaping weather systems that were both broad and powerful. The climate, as a result, had strong regional differences, not because of separation, but because of distance. Near the coasts, where the land met the surrounding ocean, conditions were often more forgiving. Moist air from the sea could roll inland, bringing rain that fed forests and wetlands. These coastal zones were rich with life. Plants grew thick and tall, forming layered canopies that sheltered insects, amphibians, and early reptiles. The ground beneath was often soft with fallen leaves and damp soil, alive with the quiet work of small creatures breaking down organic matter and returning it to the earth. Farther inland, the story grew harsher. The centre of Pangea was one of the largest continental interiors the planet has ever known. Moisture from the oceans rarely reached these regions. Clouds lost their rain long before they arrived. The result was a vast expanse of dry land, marked by deserts and semi-arid plains that stretched farther than any modern desert does today. Here, life had to be resilient. Plants adapted to conserve water, developing thick leaves, deep roots, and slow growth patterns. Animals learned to survive with limited food and shelter, often becoming more mobile, travelling long distances in search of resources. Days could be intensely hot, while nights dropped into cold that bit through even the toughest scales or fur. Despite these challenges, Pangea was not a barren world. Life had already found ways to spread across nearly every available niche. Forests of ancient conifers and seed ferns stood alongside broad plains of low-growing vegetation. Swamps and wetlands dotted low-lying areas, especially near rivers and coasts, creating habitats rich in insects, fish, and early amphibians. Above all of this moved the great reptiles and early dinosaurs that would come to define much of this era. Some were small, quick and alert, darting through undergrowth in search of insect or small prey. Others were massive, slow-moving giants that fed on tough, fibrous plants, their heavy bodies supported by thick limbs and strong bones. Predators followed the herbivores, and scavengers followed both. The land was already part of a complex web of energy and survival, long before mammals took centre stage. Every leaf, every footprint in the dust, every ripple in a shallow pool was part of a system that had been refining itself for hundreds of millions of years. Beneath this living surface, though, the planet was never truly still. Even in this period of apparent rest, Earth's interior continued its slow, restless circulation. Heat from the core rose upward through the mantle, spreading out beneath the crust before cooling and sinking again. These movements were slow beyond ordinary comprehension, but they were powerful and they were constant. The crust of Pangea sat atop this shifting foundation, like a raft on a deep, invisible sea. Most of the time, that raft felt solid. Mountains did not rise or fall in a way that would be noticeable within a single lifetime. Rivers kept their courses, forests returned year after year. To any living thing on the surface, the world seemed dependable, even permanent. Yet stress was building. The sheer size of the supercontinent played a role in this. Pangea acted like a thick blanket over parts of the mantle, trapping heat beneath it. That trapped heat made the rock below warmer and more buoyant, encouraging it to rise closer to the surface. Over millions of years, this created regions where the crust was gently pushed upward from below. At the same time, the edges of Pangea were being pulled in different directions by the movement of surrounding tectonic plates. The landmass was not a single, rigid block. It was a collection of plates fused together, each responding slightly differently to the forces beneath and around them. This combination of upward pressure from below and sideways pulling from the edges created tension. Imagine a thick sheet of ice floating on water, being pushed up from beneath while also being tugged apart from the sides. It does not crack all at once. It flexes. It bends. It forms tiny fractures that slowly grow longer and deeper. On Pangea, these early fractures took the form of long, shallow depressions in the landscape. At first, they looked like ordinary valleys. Rivers flowed through them, plants grew along their slopes, animals crossed them without any sense that these low places marked the beginning of a much larger transformation. Volcanic activity was another quiet sign of what was happening below. In some of these thinning regions, magma found pathways to the surface. Lava flowed out in broad, flat sheets, spreading across the land before cooling into layers of dark, solid rock. These eruptions were not always explosive. Often, they were steady and persistent, more like a slow leak than a violent burst. The gases released into the atmosphere during these periods had subtle but far-reaching effects. Carbon dioxide and other greenhouse gases built up, trapping heat and nudging global temperatures upward. Over time, this shifted climate patterns across the supercontinent, altering rainfall, plant growth, and the distribution of animals. Life responded as it always does, not with awareness, but with change. Species that thrived in cooler or wetter conditions began to retreat toward the coasts or higher elevations. Those better suited to warmth and dryness expanded their range. The map of ecosystems slowly redrew itself, even before any ocean had truly opened between the land masses. One of the most striking features of Pangea during this period was how connected everything still was. An animal could, in theory, migrate from what is now southern Africa to what would one day become eastern North America without ever needing to swim across an ocean. Plant species could spread their seeds across enormous distances, carried by wind, water, or wandering animals. This connectivity meant that many forms of life were widespread. Fossil records show similar species appearing on parts of the supercontinent that are now separated by vast oceans. At the time, these organisms were simply following rivers, plains, and forest corridors that stretched unbroken across the land. That broad distribution had an important effect. It kept populations mixed. Genes flowed between distant groups, maintaining a level of uniformity across huge regions. Evolution still occurred, of course, but it happened within a network of connections that slowed the process of divergence. This is part of what makes the coming separation so significant. When the land was whole, life was part of a shared system. When it began to break apart, that system would fragment, setting the stage for a burst of diversity that would reshape the living world. The skies above Pangea were quieter in some ways than today's. Birds had not yet taken to the air. The first true flying vertebrates, the pterosaurs, were beginning to appear, but they were still relatively limited in number and variety. Most of the movement happened on the ground or in the water. Insects, however, filled the air in great numbers. Dragonfly-like creatures with wingspans as wide as a human arm skimmed over swamps and rivers. Beetles, early flies, and other winged insects formed an essential part of the food web, pollinating plants, recycling organic matter, and providing meals for larger animals. The oceans surrounding Pangea were vast and deep, and their influence on the land was both subtle and powerful. Along the coastlines, tides shaped wetlands and shallow seas, creating nurseries for fish and marine reptiles. Coral reefs, though different in composition from modern ones, built up along warm, shallow waters, forming complex habitats that supported a wide range of life. Currents in Panthalassa moved heat around the globe, but without the intricate system of interconnected oceans we have today, Their patterns were simpler and broader. This contributed to the strong contrast between coastal and inland climates, reinforcing the dryness of the continental interior. As the years turned into centuries, and the centuries into millions of years, these patterns continued. Life grew, adapted, and spread across the unified land. The planet's surface changed slowly through erosion and deposition. Mountains wore down, new layers of sediment built up in lowlands and along coasts. All the while, the forces beneath the crust continued their patient work. It is easy, from a human perspective, to think of this period as a kind of golden age of stability, a time when the world was whole and unbroken. But in reality, stability on a geological scale is always temporary. Earth is a dynamic system, driven by heat, gravity, and the constant movement of its internal layers. Pangea itself was the result of earlier cycles of assembly and breakup. Before it, there had been other supercontinents, long vanished, their fragments now locked into the crust or recycled into the mantle. The world had come together before, and it would do so again in the far future. In this sense, the rest of Pangea was less like a permanent state, and more like a pause in a much longer rhythm. A moment when the pieces had gathered, settled, and held together long enough for life to flourish in a shared, connected space. As this era continued, small changes accumulated. The shallow valleys grew slightly wider. Volcanic regions became more active in certain areas. Climate zones shifted, sometimes slowly, sometimes in noticeable steps tied to bursts of geological or atmospheric change. Still, from the perspective of the creatures living through it, the world remained a single, continuous place. The idea of continents drifting apart would have made no sense, even if there had been minds capable of imagining it. What did matter to them was the availability of water, the presence of food, the safety of shelter, and the rhythms of seasons that governed breeding, migration, and growth. These daily and yearly cycles shaped their lives far more directly than the deep, hidden motions of the planet beneath their feet. For now, the supercontinent remained whole, carrying its forests, deserts, rivers, and creatures together across the slow-turning globe. A single world, resting not in stillness, but in a kind of poised balance, held between the memory of past collisions and the promise of future separation. At some point, without any announcement or sudden change in the sky, the land began to move in a way that no living thing could sense. There was no trembling underfoot, no visible sliding of hills or forests, no sound to mark the moment. The ground felt as solid as it always had. Rivers still followed their familiar courses. Trees still rooted themselves in the same soil their ancestors had known for generations. And yet, beneath all of this, the surface of the planet had entered a new phase of its long, patient journey. This was not movement in the way we usually imagine it. Nothing rushed, nothing lurched forward. The drift unfolded at a pace measured in centimetres per year, slower than grass grows, slower than most living things could ever notice. But given enough time, even the smallest motion can redraw the shape of a world. Deep below the crust, the mantle continued its slow circulation. Hot material rose, cooled, and sank again, forming immense, invisible currents that pressed against the tectonic plates above. These plates, enormous slabs of rock carrying continents, oceans, and entire ecosystems, responded to those gentle but relentless forces. Where the crust had already been weakened by heat and stretching, those forces began to take hold. Long valleys that had once been nothing more than shallow depressions started to widen. The rock along their edges cracked and slipped downward, creating steep sides and low central floors. These features are known as rift valleys, and they marked the first clear signs that the land was no longer simply resting. It was beginning to part. At first, these rifts were narrow enough that animals could cross them without much trouble. Plants still grew along their slopes. Rivers cut through them, carrying water and sediment from one side to the other. To life on the surface, they were just another feature of the landscape, no more significant than a canyon or a dry basin. But beneath those rifts, something more dramatic was happening. As the crust thinned, magma rose closer to the surface. In some places it broke through entirely, spilling out in long glowing flows that spread across the land before cooling into dark, flat plains of volcanic rock. These eruptions did not happen everywhere at once. They came in pulses, separated by long stretches of quiet. Over time, they built up thick layers of basalt, stacking one on top of another like pages in a very slow-moving book. Today, we can still see some of these ancient lava fields in places like the eastern coast of North America, parts of South America, and regions of Africa, silent records of a time when the land itself was being rewritten. Above ground, the effects of this activity were subtle, but far-reaching. Volcanic gases drifted into the atmosphere, changing its chemistry. Carbon dioxide levels rose, and with them, global temperatures edged upward. The planet did not suddenly become hot, but the balance shifted just enough to alter rainfall patterns and seasonal cycles. Some regions grew wetter as warmer air carried more moisture. Others became drier as wind patterns changed and rain was redirected elsewhere. Forests expanded in certain areas and retreated in others. Grasslands and open plains appeared where dense vegetation had once stood. Animals followed these changes, not because they understood the reason behind them, but because survival demanded it. Herds migrated toward greener regions. Predators followed their prey. Smaller creatures adapted by changing their diets, their behaviours, or their breeding patterns. All of this was happening on a landmass that was very slowly beginning to stretch and pull apart. One of the remarkable things about this drift is how uneven it was. Pangea did not split neatly down the middle. Instead, different sections moved at different speeds and in different directions, guided by the complex pattern of forces beneath them. What would one day become? North America started to edge away from what would become Africa and Europe. South America leaned gradually away from Africa. India, still attached to a larger southern landmass, began a journey that would eventually send it racing northward, long after other pieces had already gone their separate ways. At this stage, though, these movements were just the earliest hints of that future. The distances between the drifting sections were measured in meters, then kilometers, over spans of millions of years. The land was still connected, but the connections were thinning, narrowing, and weakening. In low-lying rift zones, lakes began to form. Rainwater and river runoff collected in the sunken central floors, creating long, narrow bodies of water that stretched for hundreds of kilometers. These lakes became new habitats, supporting fish, amphibians, and aquatic plants. Over time, as the rifts widened further, seawater began to creep in from the surrounding ocean. At first, this happened only during high tides or storms, when waves could push into the lowest points of the land. But gradually, permanent shallow seas formed, linking the inland waters to the open ocean. These new coastlines reshaped local climates. The presence of water moderated temperatures, making nearby regions cooler in the heat of the day and warmer at night. Moist air from the sea brought more frequent rain, encouraging the growth of vegetation along the shores. Life quickly took advantage of these changes. Coastal forests and wetlands spread along the edges of the emerging seas. Marine organisms moved into the shallow waters, while land animals learned to navigate the shifting boundary between dry ground and water. This was the beginning of a world with more edges, more borders between environments, and more opportunities for life to specialise. As the drift continued, something important happened to the movement of air and water around the planet. When Pangea had been whole, winds could sweep across enormous stretches of uninterrupted land. Ocean currents flowed in broad loops around the supercontinent, with limited pathways between different parts of the global ocean. As gaps opened and seas formed, those patterns grew more complex. Water began to circulate through the new passages, connecting regions that had previously been isolated from each other by land. These currents carried heat, nutrients, and marine life along their routes, reshaping ocean ecosystems. On land, winds met new coastlines and rising mountain ranges, forcing them upward and causing rain to fall in some places and leaving others in the shadow of dry air. This created distinct climate zones, sometimes only a few hundred kilometers apart. These changes added another layer of separation for living things. Even before the land fully broke apart, differences in climate and habitat began to limit where certain species could survive. A plant that thrived in a warm, wet coastal region might struggle in a cooler, drier interior. An animal adapted to open plains might find dense forests difficult to navigate. Over long periods, these environmental boundaries became just as significant as physical ones. They shaped migration routes, breeding grounds, and feeding areas, quietly guiding the paths of evolution. One of the most powerful effects of this slow drift was the way it began to divide populations. Imagine a species of small reptile that once ranged across a wide area of connected land. As a rift valley deepened and filled with water, part of that population found itself on one side and part on the other. At first, the separation might have been minor. Individuals could still cross the gap at narrow points or during dry seasons. But as the water widened and the land on either side continued to move apart, those crossings became less frequent and eventually impossible. Once that happened, the two groups were on their own. They experienced different climates, different predators, and different food sources. Small genetic changes that appeared in one group did not spread to the other. Over thousands and then millions of years, those differences accumulated. What began as one species gradually became two, each adapted to its own corner of the drifting world. This process did not happen just once. It happened again and again across plants, insects, reptiles, and early mammals. The slow drift of the land created a patchwork of isolated environments, each acting as a kind of natural laboratory for evolution. Some lineages flourished in these new conditions, diversifying into a wide range of forms. Others struggled and faded away, unable to keep up with the pace of change. Extinction and opportunity went hand in hand, shaping the living world in quiet, relentless ways. Meanwhile, the shape of the planet itself was changing. The supercontinent began to lose its simple outline, developing deep indentations where seas pushed inland and long arms of land where rifts had not yet fully opened. From above, it would have started to look less like a single solid mass and more like a puzzle in the early stages of being taken apart. Yet even at this point, the idea of separate continents was still far in the future. The land was stretched, cracked, and partly flooded, but connections remained. Animals could still move between most regions, and plants could still spread their seeds across broad areas. The drift was gentle, patient, and persistent. In the oceans, the effects were just as significant. The formation of new seaways allowed marine species to expand into regions they had never reached before. Fish, reptiles, and invertebrates followed currents into newly created habitats, sometimes encountering unfamiliar competitors or predators. Coral reefs grew along fresh coastlines, building complex structures that sheltered countless small organisms. Plankton populations shifted as water temperatures and nutrient flows changed, influencing the entire marine food web from the smallest filter feeders to the largest predators. These oceanic changes fed back into the atmosphere. The movement of warm and cold currents affected global climate, influencing rainfall patterns on land and the distribution of ice and snow in higher latitudes. In this way, the slow drift of the continents became part of a much larger system, linking the deep interior of the planet to the air, the water, and every living thing on the surface. One of the more subtle consequences of this process was the way it changed the rhythm of seasons in different parts of the world. As land masses shifted in latitude, regions that had once been closer to the equator drifted toward cooler zones, while others moved into warmer belts. Plants and animals had to adjust to these new patterns of light and temperature. Some developed longer or shorter growing seasons. Others altered their breeding cycles to match the timing of rains or the availability of food. These adjustments added yet another layer of variation to the story of life, creating differences not just between separate landmasses, but between regions within the same drifting piece of the world. All of this unfolded without any sense of urgency. There was no moment when the land suddenly decided to move. There was no clear beginning or end to this phase of change. It was a continuous process, driven by the same forces that had shaped the planet since its formation. From a human perspective, it is tempting to look for dramatic turning points, for events that can be marked on a timeline with a date and a name. But the slow drift of Pangea resists that kind of storytelling. It is a reminder that some of the most powerful changes in the world happen quietly, without spectacle, over stretches of time so long that they blur the line between cause and effect. If you imagine standing in one place during this era, watching the horizon day after day, year after year, you would see nothing to suggest that the land beneath you was moving. The sun would rise and set, clouds would pass, seasons would come and go, and yet, if you could return to that same spot after 10 million years, the view might be entirely different. A shallow sea might lie where there had once been a plain. A mountain range might have risen in the distance. The climate might feel warmer or cooler, wetter or drier. This contrast between the stillness of the moment and the motion of deep time is one of the most striking aspects of Earth's story. It shows how the planet can be both stable and dynamic at the same time, offering a dependable surface for life to grow and change, while slowly reshaping that surface in ways that open new paths and close old ones. As the drift continued, the connections between different parts of the land grew thinner and more fragile. Narrow land bridges became the last routes between regions that had once been fully joined. These bridges became critical pathways for migration, used by animals and plants until they too disappeared beneath rising seas or stretched beyond reach. When those final links were lost, the world crossed a quiet threshold. The supercontinent was no longer a single, continuous home for life. It had become a collection of large islands, each beginning to follow its own course. But that moment, like so many others in this story, did not arrive with fanfare. It was simply the result of countless small movements adding up over time. The land was still in the in-between state, no longer truly whole, but not yet fully divided. A world of widening gaps, shifting climates, and emerging boundaries where life was learning step by step how to navigate a planet that refused to stay still. Somewhere along the long path of separation, as the land continued to stretch and the gaps between its great pieces slowly widened, something that might seem almost contradictory began to happen. Even as parts of the world were pulling away from each other, other parts were being pushed upward. The surface of the planet, far from simply tearing open like a piece of cloth, responded to these deep forces by folding, buckling and rising into vast walls of stone. Mountains, in this phase of Earth's story, were not just the result of continents colliding, as they had been in earlier times. They also formed in places where the crust was being thinned, heated, and reshaped by the slow motion of plates sliding past, tugging apart or shifting sideways against one another. The breakup of a supercontinent is not a neat single-direction event. It is a complex, uneven process, and the land reflects that complexity in its changing shape. To understand how mountains could rise while continents drifted away, it helps to picture the crust not as a rigid shell, but as something more flexible, more responsive to stress. When you pull on a thick slab of soft clay from both ends, the middle does not always just stretch thinner. It can also wrinkle, forming ridges and folds as the material adjusts to the forces acting on it. Earth's crust behaves in a similar way, only on a scale that spans thousands of kilometers and millions of years. As Pangea began to pull apart, certain regions experienced intense pressure from the movement of plates beneath them. In some areas, plates slid past one another along long, deep faults. In others, the motion of the mantle caused sections of crust to be pushed upward, even as nearby regions sank and stretched. This created long chains of rising terrain, some of which would become the ancestors of mountain ranges that still exist today. These rising lands did not appear suddenly. There was no single moment when a flat plain turned into a jagged skyline. Instead, the process unfolded so slowly that entire ecosystems could form, change, and vanish on slopes that were themselves still in the act of becoming. At first, the land might simply have felt a little higher in some places. Rivers that once flowed lazily across wide plains found their paths altered, forced to cut deeper channels as the ground beneath them rose. Over time, those channels became valleys and gorges, carving their way through layers of rock that recorded the history of earlier landscapes. Rain and wind went to work on these new heights, almost as soon as they began to form. Softer rock wore away quickly, leaving behind harder layers that stood out as ridges and cliffs. Loose sediment washed downhill, collecting in lowlands and along coastlines, where it would eventually become the raw material for new layers of stone. This constant cycle of uplift and erosion gave the land a restless quality. Mountains were rising, but they were also being worn down at the same time. The peaks that would one day seem ancient and timeless were, their own era, part of a dynamic system that never truly paused. For life on the surface, these changes introduced a new kind of complexity. Elevation affects more than just the view. It shapes temperature, rainfall, and the types of plants and animals that can survive in a given place. As land rose, the air above it cooled. Moist air carried by winds was forced upward along mountain slopes, where it cooled further and released its moisture as rain or snow. This created wet, fertile regions on one side of a range and dry, sheltered areas on the other, a pattern known as a rain shadow. Suddenly, two places that might be relatively close together could have very different environments. One side of a rising ridge might support dense forests and flowing streams, while the other might be dry and open, with sparse vegetation and wide, sun-baked ground. These contrasts became powerful drivers of change for living things. Plants adapted to the wetter side developed different traits than those on the drier side. Animals that could move easily across open land found forests more challenging to navigate, while forest dwellers struggled in exposed plains. In this way, mountains did more than reshape the physical surface of the planet. They reshaped the paths that life could take across it. Some species found themselves effectively split by rising terrain. A population that once spread freely across a wide area might now be divided by a growing range that was too steep, too cold, or too dry to cross easily. Over time, those separated groups began to drift apart genetically, following different evolutionary paths shaped by their distinct environments. This process, known as allopatric speciation, became more common as the land grew more varied. The breakup of Pangea was not just creating oceans and seas, it was also building barriers of stone and elevation that guided the branching of the tree of life. One of the striking features of this era is how interconnected these changes were. The movement of plates beneath the crust influenced where mountains rose. Those mountains influenced where rain fell and where rivers flowed. Rivers carried sediment to the sea, shaping coastlines and shallow marine environments. The shape of those coastlines influenced ocean currents, which in turn affected climate across the land. Everything was part of a single, linked system, responding to the slow, steady pull of the planet's internal forces. In some regions, the stretching of the crust led to the formation of long, linear mountain ranges along the edges of rift zones. These ranges often ran parallel to the widening gaps in the land, marking the boundaries between sections that were moving apart. Along these boundaries, volcanic activity was common. Magma rising from below not only spilled out onto the surface, but also intruded into the crust, cooling and hardening into bodies of rock that reinforced and reshaped the surrounding layers. Over time, erosion would expose these hardened intrusions as ridges and peaks. Elsewhere, the story was different. As plates shifted, some regions experienced sideways motion rather than direct pulling apart. This kind of movement, known as strike-slip motion, created long faults where the land on either side slid past itself. Along these faults, the crust could become compressed in certain places, forcing it upward into hills and mountains. These features often formed in irregular patterns, creating complex landscapes of ridges, basins, and valleys that reflected the uneven nature of the forces at work. For animals and plants, navigating these landscapes meant dealing with a patchwork of conditions. A journey that once crossed gentle terrain might now involve climbing slopes, descending into valleys, and crossing different climate zones along the way. Some species adapted by becoming more specialized, thriving in a narrow range of conditions found at certain elevations or on specific sides of a range. Others remained more flexible, able to move between environments and take advantage of a wider range of resources. These differences in strategy influenced which lineages spread widely and which remained confined to particular regions. Mountains also played a role in shaping the planet's long-term climate. High terrain affects the circulation of air on a global scale. Large mountain ranges can deflect winds, alter jet streams, and influence where major weather systems travel. As the breakup of Pangea progressed and new ranges rose, these effects became more pronounced. Patterns of rainfall and temperature shifted across entire continents, not just in the immediate vicinity of the mountains themselves. Over millions of years, this contributed to the development of distinct climate belts, with some regions becoming consistently wetter or drier, warmer or cooler than they had been before. These broad patterns set the stage for the kinds of ecosystems that would dominate each area in the future. The impact extended into the oceans as well. Rivers flowing from rising mountains carried increased amounts of sediment to the sea. This sediment built up along coastlines and in shallow marine environments, creating new habitats for marine life. Nutrient-rich runoff from the land-fed plankton populations, which formed the base of the ocean food web. Changes in plankton communities rippled upward, influencing fish, marine reptiles, and eventually the large predators that depended on them. In this way, the growth of mountains on land could shape life far offshore, linking distant parts of the planet through the movement of water and nutrients. From a human perspective, mountains often feel like symbols of permanence, ancient features that stand unchanged through the ages. But in this chapter of Earth's history, they were signs of motion and transition. Many of the ranges that began to form during the breakup of Pangea would later be worn down, buried, or reshaped by subsequent events. Some would be uplifted again during later collisions between drifting continents. Others would fade into rolling hills and flat plains, their former heights preserved only in the rocks beneath the surface. The land was writing and rewriting its own story, layer by layer. Life too was writing its own version of that story, one shaped by the opportunities and challenges created by rising terrain. In mountainous regions, plants often developed sturdy roots to anchor themselves against erosion and steep slopes. Some evolved to grow quickly during short growing seasons, taking advantage of brief periods of warmth and moisture. Animals adapted in different ways. Some developed strong limbs for climbing or navigating uneven ground. Others learned to take advantage of the varied habitats created by changes in elevation, moving between lowlands and highlands as conditions shifted throughout the year. These adaptations added to the growing diversity of life on the planet, a diversity that was being fueled by the increasing complexity of the landscape. It is also worth remembering that these changes did not happen in isolation. The rise of mountains was happening alongside the widening of seas, the shifting of climates, and the gradual isolation of different land masses. In some regions, rising ranges formed natural boundaries that marked the edges of what would eventually become separate continents. In others, they ran through the interior of drifting plates, creating internal divisions that influenced the distribution of life within a single landmass. The world was becoming more compartmentalized, not just horizontally, through the separation of continents, but vertically, through the creation of high and low regions with their own distinct conditions. This added another dimension to the evolutionary process. Species were no longer just adapting to different latitudes or distances from the sea. They were also adapting to different heights above it. As these patterns took hold, the map of life grew more intricate. Fossil records from this period show increasing regional differences in both plants and animals. What lived in one area of the drifting world might look quite different from what lived in another, even if the two regions were still technically connected by land. These differences were the early signs of the unique biological identities that would one day define separate continents. From the perspective of deep time, the rise of mountains during the breakup of Pangea can be seen as part of a broader theme. The planet does not simply divide and spread out. It reshapes itself in multiple directions at once, creating new forms even as old ones are being pulled apart. This constant reshaping creates a kind of dialogue between stability and change. Mountains offer stable ground, long-lasting features that persist through many generations of life, but their creation is tied to the same restless forces that are tearing continents apart and opening new oceans. In this way, the solid peaks and ridges that come to define a landscape are paradoxically signs of motion. As the story continues, these rising terrains will play important roles in what comes next. They will influence where glaciers form, where rivers carve their paths, and where future collisions between drifting continents will build even greater ranges. They will also leave lasting marks on the distribution of life, shaping migration routes and creating pockets of isolation that foster further diversification. For now, the world remains in a state of unfolding. The land is pulling apart in some places and lifting itself up in others. Seas are widening, valleys are deepening, ridges are climbing higher. Life is responding, not with awareness, but with change, spreading into new habitats, retreating from others, and gradually branching into forms that reflect the growing complexity of the planet beneath it. As the land continued its slow, patient separation, something even larger than mountains began to take shape in the widening spaces between the drifting pieces of the world. Water, which had always surrounded Pangea like a single immense ring, now found new places to go. The shallow seas that had crept into low-lying rift valleys deepened. Narrow channels widened. What had once been inland lakes and flooded basins gradually connected to the open ocean, and in doing so they began the long process of becoming oceans themselves. This was not a sudden flooding, not a dramatic rush of waves breaking across the land. It was a steady, almost cautious advance. Seawater moved in as the crust sank and stretched, filling the spaces that opened between separating plates. Over thousands, then millions of years, those spaces grew wider and deeper, transforming from narrow inlets into broad, open expanses of water. From above, the shape of the planet began to change in a way that would eventually feel familiar. Long blue corridors cut into the land, separating regions that had once been directly connected. The first outlines of what would one day become the Atlantic and Indian Oceans started to appear, though at this stage they were far smaller and more enclosed than the vast bodies of water we know today. The arrival of these new seas did more than change the map. It changed how the planet moved energy. Water is an excellent carrier of heat. Warm water flows from equatorial regions toward the poles, while colder water moves back toward the equator, creating a continuous exchange that helps regulate global temperatures. When Pangea was whole, these movements were limited by the shape of the land. The great surrounding ocean could circulate freely around the supercontinent, but it had few pathways through it. As gaps opened and seas formed, those pathways multiplied. Currents began to slip between drifting land masses, finding new routes that connected distant parts of the global ocean. This set off a kind of reorganization as water adjusted to the new geography, establishing patterns that would influence climate and life for millions of years to come. At first, these currents were gentle and local. Shallow seas warmed easily under the sun and cooled quickly at night, creating small-scale movements of water driven by differences in temperature and salinity. In narrow channels, tides flowed back and forth, mixing marine life from different regions and carrying nutrients along the seafloor. Over time, as the channels widened into true ocean basins, the scale of these movements grew. Large continuous currents formed, driven by the combined effects of Earth's rotation, the shape of the coastlines, and the distribution of heat across the planet. One of the key influences here was something called the Coriolis effect, a result of the planet's rotation that causes moving water and air to curve rather than travel in straight lines. As new oceans opened, this effect began to shape broad looping patterns of circulation, some of which still exist in modified form today. These loops carried warm water away from the equator and brought cooler water back in its place, creating a global conveyor belt of heat. Regions that had once experienced extreme temperature swings began to settle into more moderate climates, especially along newly formed coastlines. Rainfall patterns changed as well. Warm currents increased evaporation, adding moisture to the air. Winds carried that moisture over nearby land, where it fell as rain, supporting forests, wetlands and river systems in areas that had previously been dry. In other regions, the opposite happened. Shifts in currents redirected warm water away from certain coasts, cooling the air above them and reducing evaporation. These areas became drier, giving rise to new deserts and semi-arid zones. For life on land, this was another layer of transformation. Plants adapted to new patterns of rainfall and temperature. Some spread rapidly into regions that had become wetter and more hospitable. Others retreated, finding refuge in pockets where conditions remained suitable. Animals followed these changes, migrating along emerging coastlines or moving inland away from drying regions. The presence of water itself became a powerful guide, shaping routes of movement and settlement. Along the shores of the new seas, entirely new environments formed. Tidal flats appeared where the land sloped gently into the water. Mangrove-like forests and coastal wetlands took root in warm, shallow areas, creating rich habitats that supported a wide range of species. These coastal zones became some of the most productive ecosystems on the planet. Nutrients washed down from the land by rivers mixed with mineral-rich seawater, fueling the growth of plankton. Small fish and invertebrates fed on the plankton, and larger predators followed, creating complex food webs that extended from microscopic organisms to the largest marine reptiles of the time. The opening oceans also changed the chemistry of the water itself. As new basins formed, they interacted with fresh rock exposed by rifting and volcanic activity. Minerals dissolved into the seawater, altering its composition and influencing which organisms could thrive there. Some marine species found these conditions favourable and spread quickly through the new passages. Others struggled to adapt, disappearing from regions that no longer met their needs. This selective pressure drove evolution in the oceans just as it did on land. Isolated basins and changing currents created pockets of unique conditions, encouraging the development of distinct communities in different parts of the expanding seas. In certain areas, shallow waters became nurseries for young marine animals, protected from large predators by complex coastlines and underwater structures. Coral-like organisms built reefs along the edges of drifting landmasses, forming barriers that shaped waves, currents, and sediment flow. These reefs in turn influenced the shape of the coast. They broke the force of incoming waves, allowing fine sediment to settle and build up beaches and lagoons behind them. Over time, this created chains of islands and sheltered bays, adding even more variety to the marine landscape. The interaction between land and sea grew increasingly intricate. Rivers carried not just water, but also nutrients and organic matter from inland regions to the coast. This runoff supported rich plant and plankton growth, which fed marine food webs. At the same time, the sea influenced the land through storms and tides. Waves eroded cliffs and headlands, carrying sediment away to be deposited elsewhere. Coastal plains expanded and contracted as sea levels rose and fell, in response to global climate changes. These processes blurred the boundary between land and ocean, creating transitional zones where both terrestrial and marine life could find a place. One of the most important long-term effects of the opening oceans was the way they changed the planet's ability to store and move carbon. The oceans absorb large amounts of carbon dioxide from the atmosphere, storing it in dissolved form or locking it away in the shells of marine organisms and in sediments on the seafloor. As new ocean basins formed, they increased the total area of water available for this exchange. Over time, this helped regulate atmospheric carbon levels, influencing global temperatures and climate stability. This, in turn, affected life on land and in the sea. Cooler or warmer periods altered the distribution of ecosystems, pushing species to adapt, migrate, or face extinction. The oceans also became highways for life. Marine organisms could now travel long distances along continuous coastlines and through open waters, spreading their populations across wide areas. This connectivity allowed some species to become globally distributed, while others remained confined to specific regions where currents or temperature barriers limited their movement. The contrast between widespread and localized species became another driver of evolutionary diversity. On land, the presence of oceans introduced new influences as well. Coastal regions experienced more stable temperatures than deep inland areas, as water moderated both heat and cold. This stability allowed certain plants and animals to thrive year-round, creating refuges during periods of broader climate stress. In times when the planet grew hotter or colder, these coastal zones often acted as shelters, preserving lineages that might have disappeared elsewhere. When conditions improved, those lineages could spread outward again, repopulating regions that had been temporarily inhospitable. The slow opening of oceans, then, did not just divide the land. It created a dynamic system of connection and refuge, movement and stability that shaped the resilience of life across the planet. There was also a quieter, less visible change happening deep below the surface. As continents moved apart and new oceanic crust formed between them, magma rose from the mantle and cooled into solid rock at the spreading centres. This newly formed crust was different from the older continental crust. It was denser, thinner, and constantly being recycled. As it moved away from the spreading centres, it cooled and sank slightly, contributing to the depth of the growing ocean basins. Farther away, older oceanic crust eventually slid back into the mantle at subduction zones, where one plate was forced beneath another. This recycling of material helped drive the continued motion of the plates, keeping the entire system in motion. These deep processes were invisible from the surface, but their effects were everywhere. The shape of the seafloor influenced the paths of deep ocean currents. Underwater ridges and basins guided the flow of cold, dense water that moved slowly along the bottom of the oceans, carrying oxygen and nutrients to the depths. These deep currents supported life far below the reach of sunlight, creating ecosystems around chemical-rich vents, and in dark, cold environments where organisms relied on entirely different energy sources than those on the surface. The opening oceans, then, were not just spaces of water. They were layered systems, from sunlit surface waters teeming with plankton to dark abyssal plains shaped by the slow movement of deep currents and the steady rain of organic material from above. For the planet as a whole, this added a new level of complexity. Energy flowed through the system in more varied ways. Heat, carbon, nutrients, and life itself moved along pathways that had not existed before. This complexity made the Earth more dynamic, but also more stable in the long run. The interconnected system of oceans and continents helped buffer the planet against extreme swings in climate, allowing life to persist through periods of change. From the perspective of deep time, the opening of oceans during the breakup of Pangea can be seen as the creation of a new circulatory system for the planet. Just as blood carries oxygen and nutrients through a body, ocean currents began to carry heat and life across the globe, linking distant regions into a single responsive whole. Life adapted to this new system in countless ways. Some species evolved to follow currents, drifting as larvae across wide stretches of water before settling in distant habitats. Others developed forms and behaviours suited to life in specific temperature zones or depths. On land, plants and animals near the coast learned to cope with salt spray, shifting sands and periodic flooding. Some turned these challenges into opportunities, developing traits that allowed them to thrive in environments that others could not tolerate. All of this unfolded gradually without any clear dividing line between what came before and what came after. The land did not suddenly become a collection of separate continents, and the water did not instantly become the modern oceans. Both were in the process of becoming, shaped by forces that worked on timescales far beyond ordinary experience. As the currents settled into their new paths, they began to set patterns that would persist, with variations for millions of years. These patterns would influence where ice formed in colder periods, where rain fell in warmer ones, and where life found its most stable homes. The world was learning how to move itself in a new way, guided by the flow of water as much as by the movement of stone. As the oceans widened and the pathways of water settled into their new looping routes, the air above them began to change as well. Climate, which had once been shaped largely by the sheer size and unbroken sweep of Pangea, now found itself responding to a world that was becoming increasingly divided. Land and sea no longer formed a single dominant pattern. Instead, they worked together in more intricate, sometimes unpredictable ways, shaping the rhythms of temperature, rainfall, and season across the drifting pieces of the planet. In the time when the supercontinent was whole, climate zones tended to stretch in broad bands. The interior of the landmass was dry and extreme, while the edges were moderated by the surrounding ocean. But as new seas opened and coastlines multiplied, that simple arrangement gave way to a mosaic of regional climates, each influenced by its own combination of latitude, elevation, proximity to water, and the direction of prevailing winds. Warm ocean currents carried heat away from the equator and released it into the air along certain coasts, creating mild, damp conditions even in regions that lay far from the tropics. Cold currents flowed down from higher latitudes, chilling the air above them and producing cooler, drier climates in places that might otherwise have been warm and wet. These contrasts became sharper as the continents continued to drift. A stretch of land that had once shared similar weather with its neighbour across a broad plain now found itself facing an ocean on one side and a rising mountain range on the other. The winds that reached it had travelled different paths, crossed different waters, and picked up different amounts of heat and moisture along the way. The result was a growing sense of separation, not just in space, but in time as well. Seasons began to diverge. The timing of rains, the length of winters, and the intensity of summers varied more widely from region to region. In one part of the drifting world, forests might flush with new growth as seasonal rains arrived, while in another, plants waited through long, dry months for a brief window of moisture. Animals adapted their breeding and migration cycles to these local rhythms, tying their lives to patterns that no longer match those of distant relatives. Latitude played an increasingly important role in shaping these differences. As continents moved northward or southward, they crossed into different bands of sunlight. Regions closer to the equator received more direct, consistent sunlight throughout the year, leading to warmer temperatures and, in many cases, higher levels of rainfall. Farther from the equator, sunlight arrived at a lower angle and varied more dramatically between seasons. This created stronger contrast between summer and winter, with longer days and warmer temperatures in one part of the year, and shorter, colder days in another. Plants and animals that had evolved under relatively stable conditions now faced new challenges. Some species were able to adjust their life cycles, developing ways to survive colder winters or take advantage of short, intense growing seasons. Others found the changes too severe and retreated toward more suitable climates, or disappeared entirely. The opening oceans also introduced new sources of moisture into the atmosphere. Evaporation from the sea added water vapour to the air, which winds carried over land before releasing it as rain or snow. Where this moisture fell depended on the shape of the coastlines, the height of the land, and the direction of the prevailing winds. In some regions, this created lush, wet climates where dense vegetation could thrive. Rivers grew larger and more reliable, carving deep channels through the land and feeding wetlands and floodplains. In other regions, mountain ranges blocked the flow of moist air, forcing it to rise and drop its rain on one side, while leaving the other side in a dry shadow. These rain shadow zones became some of the most arid places on the planet, home to deserts and sparse grasslands. This patchwork of wet and dry areas added yet another layer of complexity to the world. It shaped where forests could grow, where open plains would dominate, and where life had to adapt to scarcity. One of the quieter but significant shifts involved the timing and predictability of seasons. When Pangea was whole, the vast size of the landmass created strong seasonal patterns driven by the heating and cooling of the continental interior. Large areas experienced dramatic differences between hot summers and cold winters, with winds reversing direction as the land warmed and cooled. As the land broke apart, these large-scale continental patterns weakened. Smaller land masses responded more quickly to the influence of the surrounding oceans, which tend to change temperature more slowly than land. This moderated seasonal extremes in many coastal regions, leading to milder winters and cooler summers. At the same time, interior regions of the newly formed continents could still experience strong seasonal swings, especially where mountains and distance from the sea limited the moderating influence of ocean air. This created a world where two places at similar latitudes could have very different seasonal experiences depending on their geography. One region might enjoy steady, moderate temperatures year-round, while another, not far away, might swing between freezing winters and scorching summers. For living things, these differences mattered deeply. The timing of flowering, the availability of food, and the length of breeding seasons all depended on local climate patterns. In regions with predictable seasons, many plants evolved to grow, flower, and produce seeds during specific windows of the year. Animals timed their migrations and reproduction to coincide with periods of abundance. In more variable climates, flexibility became an advantage. Species that could adjust their behavior or diet in response to changing conditions were more likely to survive than those tied to narrow seasonal cues. Over time, these pressures contributed to the growing diversity of life across the drifting continents. Different regions became home to different communities, each shaped by its own climate rhythms. The oceans themselves played a role in amplifying some of these differences. Large bodies of water store and release heat slowly, creating lag effects in seasonal cycles. Coastal areas often experienced delayed summers and winters compared to inland regions at the same latitude. This meant that plants and animals near the coast might respond to the seasons at different times than their inland counterparts. Even within the same species, populations in different locations could develop slightly different life cycles, further contributing to genetic divergence over long periods. Another factor in this changing climate system was the distribution of ice. As continents drifted into higher latitudes, some regions became cold enough to support seasonal or even permanent ice. Snow and ice reflect more sunlight than darker land or water, sending a portion of incoming energy back into space. This can cool the surrounding region, reinforcing colder conditions and allowing ice to persist and expand. In areas where this feedback took hold, climates shifted toward colder, more stable patterns. Glaciers formed in high mountain ranges and in polar regions, carving valleys and shaping the land as they moved. The presence of ice also influenced sea levels. When large amounts of water were locked up in ice on land, sea levels fell, exposing continental shelves and creating land bridges between regions. When the ice melted, sea levels rose again, flooding those connections and restoring separation. These cycles of connection and isolation added another dimension to the story of life. During periods of low sea level, animals and plants could spread across newly exposed land. When the water returned, those populations were cut off once more, continuing the process of divergence. The interaction between climate and geography became a kind of slow, repeating pattern, opening and closing doors for migration and adaptation. Wind patterns too grew more complex as the world became more divided. The shape and orientation of continents influenced how air moved around the globe. Large land masses could redirect major wind belts, creating zones of rising and sinking air that affected where rain fell. As the continents shifted, these wind patterns shifted with them. Regions that had once been under steady, moist winds might find themselves in zones of dry, descending air. Others might suddenly receive more frequent storms and heavier rainfall. These changes did not happen everywhere at once. They unfolded unevenly, creating a sense of unpredictability in the environment. For life, this meant that stability could no longer be taken for granted. Some species adapted by becoming more generalist, able to survive in a wide range of conditions. Others became specialists, thriving in very specific climates but struggling when those conditions changed. The fossil record from this period reflects these patterns. In some regions, a wide variety of species appeared and persisted, suggesting environments that supported diverse communities. In others, turnover was high, with species appearing and disappearing more rapidly as conditions fluctuated. Plants, as the foundation of most ecosystems, were often the first to respond to climate shifts. Changes in temperature and rainfall could alter which species dominated a region, reshaping the entire food web. For example, a shift toward drier conditions might favour grasses and shrubs over large, broad-leaved plants. This, in turn, would benefit grazing animals and disadvantage those that fed on leaves or fruit. Predators followed their prey, and scavengers followed the predators. In this way, a change in climate could ripple through an ecosystem, affecting every level. The separation of climates also influenced the chemistry of the land and water. Increased rainfall in some areas led to more intense weathering of rocks, releasing minerals into soils and rivers. These minerals supported plant growth and were carried to the oceans, where they influenced marine life. In drier regions, soils developed differently, often accumulating salts and other compounds that limited the types of plants that could grow there. This created further contrasts between neighbouring regions, reinforcing the sense of ecological separation. One of the most far-reaching consequences of these climate shifts was the way they shaped long-term evolutionary trends. Regions with stable, moderate climates often acted as refuges, allowing lineages to persist through periods of broader environmental change. More extreme regions, on the other hand, became arenas of rapid adaptation. Species that could not keep up with changing conditions disappeared, while those that could adapt quickly gave rise to new forms. Over millions of years, this combination of stability and challenge helped drive the diversification of life, creating the rich variety of plants and animals that would later populate the modern continents. It is also worth noting that these changes did not move in a straight line. Climate on Earth has always been influenced by multiple factors, including volcanic activity, changes in the planet's orbit, and variations in solar energy. The opening oceans and drifting continents added another powerful set of influences, interacting with these broader forces in complex ways. Periods of warming and cooling overlapped with the slow reorganization of land and sea, producing patterns that were anything but simple. From the perspective of deep time, though, a general trend is clear. The breakup of Pangea led to a world of greater climatic diversity. Instead of a few broad zones, the planet developed a wide range of local conditions, each with its own seasonal rhythm and ecological character. This diversity created more opportunities for life to specialize, adapt, and branch into new forms. Imagine standing on one of these drifting continents during this era. In one direction, you might see a coastline washed by warm currents, with moist air drifting inland and feeding forests and rivers. In another, you might face a mountain range that blocks those winds. beyond which lies a dry, open landscape shaped by sun and scarcity. Travelling between these regions would be like moving between different worlds, each with its own rules and rhythms. For animals, these transitions could be both challenges and opportunities. A species that could move across multiple climate zones might find new food sources and escape competition. One that was tied to a narrow set of conditions might find its world shrinking as those conditions shifted. Plants faced similar choices, though their movement was slower and depended on seeds carried by wind, water, or animals. Some species spread widely along new corridors of favourable climate. Others became confined to isolated pockets, where they evolved in relative isolation. These patterns set the stage for the distinct biological identities that would later define separate continents. The plants and animals of one region increasingly differed from those of another, not just because of physical separation, but because they lived under different skies, different rains, and different seasons. The idea of a shared global climate gave way to a more fragmented reality, where each part of the world followed its own environmental story. And yet, even in this growing diversity, there was still connection. Ocean currents linked distant coasts. Migratory animals carried seeds and nutrients across regions. Atmospheric circulation tied the fate of one climate zone to another, sending storms and dry spells along vast pathways. The planet remained a single, interconnected system, even as its surface grew more divided. As this process continued, the contrast between regions became more pronounced. Some areas settled into patterns that would, with further change, resemble modern tropical, temperate or arid climates. Others remained in transitional states, shifting back and forth as continents continued their slow drift. These evolving climates would play a crucial role in what came next. They would influence where different groups of animals could survive, which plants could take root, and how ecosystems assembled themselves on the moving pieces of the world. By the time the climates of the drifting world had begun to settle into their own regional rhythms, something subtle but deeply influential was happening to the living things that called this changing planet home. The land, once a single, continuous stage for migration and expansion, had quietly transformed into a series of moving platforms, not always surrounded by open water, not always clearly separated by visible boundaries, but increasingly isolated by a combination of distance, climate, rising terrain, and widening seas. These were not islands in the simple, familiar sense of a patch of land ringed by waves. They were ecological islands, regions of habitat cut off from one another by barriers that living things could not easily cross. A stretch of desert might be as impassable to a forest-dwelling animal as an ocean. A cold mountain range could block the path of a plant adapted to warm lowlands just as effectively as a wide channel of water. As the breakup of Pangea continued, the world became a mosaic of these drifting, shifting islands of life. Imagine a population of animals that once ranged across a vast connected plain. Their ancestors had spread freely, following rivers, grazing on open land, and mixing with other groups across enormous distances. Over time, a shallow sea crept in, dividing the plain into two long peninsulas. Then, a rising ridge cut across one of those peninsulas, creating a cooler, wetter region on one side and a drier, warmer region on the other. What had once been a single, shared habitat became three distinct worlds, each with its own conditions and challenges. At first, individuals might still have crossed these new boundaries. During dry seasons, they might have walked across narrow land bridges. During cooler periods, they might have ventured into higher terrain. But as the seas widened, the climates diverged, and the mountains rose, those crossings became less frequent. Eventually, they stopped altogether. From that moment on, the fate of each group was tied to its own piece of the drifting planet. They ate different food, faced different predators, endured different temperatures and rainfall patterns. Even the length of their seasons began to differ. Small genetic changes that arose in one group stayed there. Over many generations, those changes accumulated, shaping bodies, behaviours, and life cycles in ways that reflected the unique demands of each island. This is one of the most powerful engines of evolution. Isolation does not just separate populations, it gives them the freedom to become something new. Plants experience the same process, though in a quieter, slower way. Seeds that once spread across wide areas found their paths blocked by water, mountains, or stretches of inhospitable climate. A tree species that had once formed continuous forests might now exist in scattered patches, each adapting to slightly different conditions. In a wetter region, leaves might grow broader to capture light under thick cloud cover. In a drier one, they might become smaller or thicker to conserve water. Roots might reach deeper in one place and spread wider in another. Over time, these differences could become so pronounced that the plants were no longer the same species, even if they still resembled one another at a glance. Insects, often carried by wind or by other animals, sometimes managed to bridge these gaps, spreading genes between isolated regions. But even they were influenced by the shifting patterns of climate and geography. A cold mountain range or a wide dry basin could limit their movement just as effectively as a body of water. For many animals, especially those tied closely to specific habitats, the sense of being trapped was not something they experienced consciously. They simply lived within the boundaries of what was possible for them. But from the perspective of deep time, those boundaries were shaping the future of life in profound ways. Some of these ecological islands were relatively stable. Coastal regions with mild, predictable climates often remained hospitable for long periods. These areas became refuges, places where lineages could persist even when conditions elsewhere grew harsher. Inland regions, by contrast, were often more vulnerable to change. Shifts in rainfall or temperature could quickly turn a once productive area into a difficult place to survive. Populations living in these regions faced repeated challenges, and only those that could adapt quickly or move on managed to endure. This created a kind of uneven pattern across the drifting continents. Some regions became cradles of diversity, where many different forms of life developed and coexisted. Others became filters, where only a few highly adapted species could persist. The oceans added another layer to this pattern. As seas widened, true islands formed in addition to the ecological ones. Pieces of land broke away completely, surrounded by water on all sides. These real islands became some of the most intense laboratories of evolution on the planet. On a small, isolated landmass, resources are limited. Space is limited. The number of species that can live there is constrained by what the environment can support. This often leads to dramatic changes in the organisms that do manage to establish themselves. Large animals may become smaller over generations, a phenomenon known as island dwarfism, because there simply is not enough food to support their original size. Smaller animals may grow larger, taking on roles that would be filled by bigger species on a continent, a process called island gigantism. Predators may lose their fear of larger animals if none exist. Prey species may evolve new defences if there is no easy way to escape. Birds may lose the ability to fly if they no longer need to travel long distances or avoid ground-based threats. While many of the classic examples of these patterns come from much later in Earth's history, the groundwork for them was being laid during this era of drifting land and widening seas. Even on larger land masses that were not fully isolated by water, the same principles applied. A population cut off by climate or terrain experienced a similar set of pressures, just on a different scale. One of the quieter but important effects of this growing isolation was the way it shaped behaviour. Animals in different regions began to develop different strategies for survival, even if they shared a common ancestry. In a region with predictable seasons, migration might become a regular part of life. In a more stable environment, staying in one place year-round might be more efficient. Some species became more social, forming groups to defend limited resources or care for young in challenging conditions. Others became more solitary, reducing competition by spreading out across large territories. These behavioural differences, once established, could reinforce physical and genetic separation. Animals that did not interact rarely bred, and over time, this reduced the flow of genes between populations even further. The plants and animals living on these moving islands were also influenced by chance in powerful ways. When a new habitat formed, such as a freshly exposed coastline or a newly uplifted plateau, the first species to arrive often had a lasting impact on what followed. These early arrivals could shape the environment, making it more or less hospitable for other species. For example, a plant that stabilized soil and added organic matter could pave the way for a whole community of other plants and animals. A predator that arrived early could limit which prey species managed to establish themselves. This element of chance meant that two regions with similar climates and geography could develop very different ecosystems, simply because different species happened to get there first. Over millions of years, this led to a growing patchwork of biological identities across the planet. The plants and animals of one drifting piece of land began to look increasingly distinct from those of another, even if the environments themselves were not dramatically different. This is why, in the modern world, different continents often have their own characteristic groups of animals and plants. Marsupials dominate in Australia. Large, hoofed mammals are common in Africa. Unique birds and reptiles define many island chains. The roots of that pattern lie in this long period of separation and isolation, when life was being sorted region by region by the slow movement of the land. It is also important to remember that isolation was not always permanent. Sea levels rose and fell as climate changed. During cooler periods, when more water was locked up in ice, sea levels dropped, exposing continental shelves and creating temporary land bridges. These bridges allowed animals and plants to cross between regions that had been separated by water. When the climate warmed and the ice melted, the sea returned, cutting off those routes once more. Each cycle of connection and separation mixed and then remixed the living world, adding complexity to the patterns of distribution and evolution. Some species took advantage of these windows, spreading into new territories and establishing themselves before the door closed again. Others missed the opportunity and remained confined to their original regions. This process added a kind of rhythm to the story of life, a slow opening and closing of pathways that shaped who could go where and when. The oceans themselves were not just barriers, they were also corridors for certain forms of life. Marine organisms drifting as larvae or swimming with currents could cross vast distances, connecting distant coastlines in ways that land animals could not. This meant that some marine species maintained a global presence even as land-based species became increasingly regional. In coastal areas, this led to interesting interactions. A shoreline might host land animals and plants that were highly specific to that region, alongside marine life that was part of a much broader, more connected system. This contrast highlighted the different ways in which isolation and connection operated on land and in the sea. Another consequence of life being confined to moving islands was the way it influenced extinction. Small, isolated populations are often more vulnerable to sudden changes. A drought, a disease, or a new predator can have a much larger impact when there are few individuals and limited opportunities to move elsewhere. During this era, regions that were cut off and environmentally unstable experienced higher rates of turnover. Species appeared, adapted, and disappeared more quickly than in larger, more stable areas. This process, while harsh on individual lineages, contributed to the overall dynamism of the living world. It cleared space for new forms to arise and for successful adaptations to spread. At the same time, stable regions acted as reservoirs of older lineages, preserving forms of life that might otherwise have vanished entirely. This balance between change and persistence is one of the defining features of Earth's biological history, and the breakup of Pangea played a major role in shaping it. From the perspective of a single animal or plant, the world was simply the place it lived. It did not know it was on a drifting piece of a former supercontinent. It did not know that its distant relatives were evolving along different paths on other parts of the world. It responded to what was immediate and tangible: the availability of food, the presence of shelter, the pattern of light and dark, wet and dry, warm and cold. But when you step back and look at the story as a whole, you can see how those local experiences were part of a much larger process, one that was slowly dividing the living world into separate chapters, each written on a different piece of the planet. This division did not just create differences, it created opportunities. In isolation, unusual traits that might be overwhelmed or outcompeted in a large, connected population could persist and develop. A new way of feeding, a different body shape, or a unique reproductive strategy could take hold and define a lineage. Some of these experiments failed, others succeeded spectacularly, giving rise to groups of organisms that would dominate their regions for millions of years. As the moving islands of life continued their slow journeys, the planet became a place of increasing variety. Forests in one region bore little resemblance to those in another. Animals in distant lands developed forms and behaviours that reflected their unique histories. The world was no longer a single shared stage. It was a collection of stages, each with its own cast and its own script, shaped by the same underlying forces but played out in different ways. At a certain point in this long, quiet process of separation, something began to change in the way life responded to the world around it. The land was no longer just drifting. The climates were no longer just shifting. The populations of plants and animals, now living on their own moving stages of land and sea, were starting to follow paths that led them in very different directions. Evolution, which had always been present as a steady background force, became more visible in its outcomes, not because it sped up in any dramatic sense, but because the conditions shaping it had grown more varied. The world was offering different answers to the same basic questions of survival, and life was beginning to explore those answers in ways that no longer looked the same from one region to the next. Imagine two populations of the same animal, once part of a single connected group. One now lives in a warm, wet region near a new coastline where food is plentiful year-round and temperatures rarely drop too low. The other lives farther inland, in a place where seasons are more extreme, with long dry periods followed by short bursts of rain and growth. Both populations face the same fundamental needs. They must find food, they must avoid predators, they must reproduce. But the strategies that work best in one place do not necessarily work in the other. In the coastal region, being active year-round might be an advantage. There is always something to eat, always somewhere to shelter. In the inland region, conserving energy during dry or cold periods might be more important, with bursts of activity timed to coincide with short seasons of abundance. Over generations, these differences in lifestyle begin to leave their mark on bodies and behaviours. The coastal population might develop traits that favour constant movement and foraging. The inland group might evolve features that help it store energy, tolerate heat, or survive with limited water. At first, these differences are subtle, a slightly different body size, a change in the shape of a limb or a tooth, a shift in breeding season by a few weeks. But given enough time, those small changes accumulate. Eventually, if the separation continues, the two populations may no longer be able to breed with each other, even if they were somehow brought back together. At that point, they have become different species, each shaped by the particular road it has taken through the changing world. This process did not happen in just one pair of populations. It happened across countless groups of plants, insects, reptiles, and early mammals, scattered across the drifting pieces of the former supercontinent. Some regions became places where evolution explored certain themes again and again. In open, grassy, or semi-arid areas, for example, animals often developed longer legs and more efficient ways of moving across wide spaces. Speed and endurance became valuable traits. In dense forests, by contrast, agility and the ability to climb or move through tangled vegetation became more important. Smaller body sizes, grasping limbs, and keen senses offered advantages in these complex environments. These patterns repeated themselves in different parts of the world, but with local variations. A climbing animal in one region might look quite different from a climbing animal in another, even if both filled a similar ecological role. This is one of the fascinating results of evolution taking different roads. The same kind of problem, such as how to reach food high in trees, can lead to very different solutions, depending on the materials and history available in a given place. Plants followed their own branching paths. In regions with frequent rainfall, tall, fast-growing plants often dominated, competing for sunlight by reaching higher and spreading broader leaves. In drier regions, shorter, tougher plants became more common, conserving water and surviving in soils with fewer nutrients. Some developed thick coatings on their leaves to reduce evaporation. Others grew deep root systems that tapped into water far below the surface. Even in similar climates, different plant lineages took different approaches. Some relied on seeds that could survive long periods of drought. Others spread through underground stems that allowed them to regrow quickly after harsh conditions passed. These varied strategies shaped the landscapes themselves. The structure of a forest or grassland influences how fire spreads, how water flows, and how animals move through the area. In this way, the evolutionary paths of plants and animals became intertwined, each influencing the direction of the other. One of the most important aspects of this period was the increasing role of specialization. In a large, connected world, being a generalist can be a successful strategy. A species that can eat many different foods, tolerate a wide range of conditions, and move across large areas has more options when something changes. But in a world of isolated regions and distinct climates, there are advantages to becoming very good at one particular way of living. A plant that is perfectly suited to a specific soil type or rainfall pattern may outcompete others in that niche. An animal that is finely tuned to hunt a particular kind of prey in a particular environment may thrive where more generalist predators struggle. As the continents drifted and regions became more distinct, these specialized forms of life began to appear more often. Some animals developed teeth and jaws, adapted to very specific diets. Others evolved body shapes that matched the demands of their environment with remarkable precision. Insects specialized in feeding on particular plant species, and those plants in turn evolved defenses tailored to the insects that fed on them. This back and forth, often called coevolution, became more pronounced as populations remained in close contact with the same partners and competitors over long periods of time. In one region, a certain type of flowering plant might develop a relationship with a specific pollinating insect. The shape of the flower and the body of the insect become matched, each influencing the evolution of the other. In another region, a similar plant might form a partnership with a completely different kind of pollinator, leading to a different set of traits. These localized relationships added to the growing sense that each part of the world was developing its own ecological character. The separation of populations also made chance a more powerful force. In a large connected population, a new trait that appears in a few individuals may be diluted or lost if it does not offer a clear advantage. But in a small, isolated group, that same trait can become common simply because there are fewer individuals to balance it out. This is known as genetic drift, and it can lead to significant differences between populations even in the absence of strong environmental pressures. Imagine a small group of animals becoming isolated on a newly formed landmass. By chance, a higher proportion of them might carry a gene for a particular fur colour, body size or behaviour. As they reproduce, that trait becomes common in the population, not because it is especially useful, but because it happened to be present in the founding group. Over time, these chance differences can combine with natural selection, producing unique combinations of traits that would be unlikely to arise in a larger, more connected population. This is one of the reasons why island and isolated region species often look so distinctive. During this era of drifting continents, many regions effectively functioned like islands, even if they were not fully surrounded by water. The combination of distance, climate, and terrain created small worlds within the larger one, where evolution could explore unusual directions. Some of these directions led to remarkable success. Lineages that adapted well to their local conditions expanded and diversified, filling a range of related roles within their ecosystems. Others led to dead ends. A highly specialized species might thrive for a time, but if conditions changed, it could find itself with no easy way to adapt. In these cases, extinction followed, clearing the way for other forms to take its place. This pattern of branching and pruning is a constant feature of life's history, but the breakup of Pangea amplified it by increasing the number of separate arenas in which it could play out. Another important shift involved the movement of early mammals. For much of this period, mammals were still relatively small and often lived in the shadows of larger reptiles and dinosaurs, but they were also highly adaptable, capable of exploiting a wide range of food sources and habitats. As regions became more isolated and climates more varied, mammals began to explore different ways of living. Some became more adept at burrowing, using the soil as a refuge from predators and extreme temperatures. Others took to the trees, developing traits that allowed them to climb and move through branches. Still others remained ground dwellers, focusing on speed, endurance, or the ability to process tough plant material. These early experiments did not yet produce the wide range of mammal forms we see today, but they laid the groundwork for what would come later, when the disappearance of the dinosaurs opened up even more opportunities. Reptiles and dinosaurs also followed different evolutionary paths in different regions. In some areas, large herbivores dominated open landscapes, shaping vegetation through their feeding habits. In others, smaller, more agile forms were more common, navigating complex environments like forests and wetlands. Predators adapted in response, evolving different hunting strategies, body sizes and sensory abilities depending on the prey available to them. The oceans too were arenas of divergent evolution. As new basins formed and currents established distinct temperature zones, marine species adapted to local conditions. Some thrived in warm, shallow waters, developing forms suited to reef environments and coastal habitats. Others specialized in colder, deeper regions, where light was scarce and food arrived mainly as a slow rain of organic material from above. Isolation in the oceans could be just as powerful as on land. A current that flowed in a particular pattern could keep populations separated, even if there was no obvious physical barrier between them. Over time, this led to the development of regional marine communities, each with its own characteristic mix of species. One of the more subtle but significant effects of these diverging paths was the way they influenced the pace of change. In some regions, conditions were relatively stable over long periods. Here, evolution tended to proceed more slowly, with species maintaining similar forms for millions of years. In more dynamic regions, where climates shifted frequently or landscapes changed rapidly, evolution often moved faster. Populations faced repeated challenges, and those that could adapt quickly were more likely to survive. This uneven pace of change meant that different parts of the world were, in a sense, living in different evolutionary times. At any given moment, one region might be home to species that had changed little for a very long time, while another might be filled with recently evolved forms still exploring new ways of living. These differences added to the overall complexity of the global ecosystem, creating a patchwork of old and new, stable and dynamic, all coexisting on the same planet. It is also worth considering the role of movement, even in a world of growing isolation. While many populations became confined to their local regions, others retained the ability to travel long distances. Birds, flying insects, and marine animals could cross barriers that land dwellers could not. These mobile species acted as connectors, carrying seeds, nutrients, and sometimes even other organisms between distant regions. This helped maintain a degree of global connection, even as the continents drifted apart. The influence of these travellers was uneven. Some regions received frequent visitors, while others remained largely isolated. This added another layer of variability to the evolutionary process. In places with regular connections, gene flow between populations could slow the pace of divergence. In more isolated areas, differences could accumulate more quickly. The result was a world where evolution moved along many different roads at once, some wide and well-travelled, others narrow and winding. The idea of a single, shared evolutionary path for all life on Earth became less and less accurate. Instead, the living world began to resemble a branching network, with each branch shaped by its own history of movement, isolation, and adaptation. From a distance, this network might look chaotic, but when you look more closely, patterns emerge. Regions with similar climates and landscapes often produce similar kinds of life, even if those life forms were not closely related. This phenomenon, known as convergent evolution, highlights how the environment can guide the direction of change. For example, in different parts of the world, animals that lived in open grasslands often developed similar body shapes and behaviours, even if their ancestors were quite different. The demands of running across wide, exposed spaces and spotting predators from a distance led to comparable solutions. In forested regions, climbing animals in different lineages developed grasping limbs and keen senses, again reflecting the influence of a shared set of challenges. These recurring themes added a sense of coherence to the growing diversity of life. Even as evolution took different roads, those roads often led to familiar destinations, shaped by the basic requirements of living on a planet with gravity, sunlight, and limited resources. Still, the details mattered. The exact forms that emerged in one region were never quite the same as those in another. Each place carried the imprint of its own unique history, a record of which species arrived first, which conditions persisted, and which challenges proved most significant. This growing regional identity set the stage for some of the most dramatic chapters in Earth's biological story. As the continents continued to drift and the climates continued to change, the living world was becoming increasingly diverse and increasingly localized. For now, though, the world remains in this rich, complex phase of exploration. Life is trying out new shapes, new behaviours, and new relationships, guided by the many different landscapes and climates of a planet that is still in the process of becoming. Each drifting landmass, each isolated region is writing its own version of the story, adding a new thread to the vast interconnected tapestry of Earth's living history, a tapestry that continues to grow, branch, and change. Long before the word dinosaur would ever be spoken, before bones were studied and named and placed behind museum glass, these animals were simply part of the everyday world. They walked across floodplains, browsed in forests, and hunted along riverbanks without any sense that they would one day become symbols of deep time. In the era when the land was pulling itself apart, they were not relics of a vanished age. They were the present. As the continents continued to drift, the great reptiles that dominated much of the land found themselves living on a planet that was quietly changing beneath their feet. The broad, continuous ranges that had once allowed herds and predators to move across vast distances were becoming narrower. Pathways that had once been open plains were now broken by rising ridges, widening seas, and shifting climate zones. For many dinosaur species, this meant that the world was becoming more local. A herd that once followed seasonal rains across a wide stretch of connected land might now be confined to a single drifting region. A predator that once ranged across multiple habitats might find its hunting grounds reduced by new barriers it could not easily cross. These changes did not happen overnight. Generations of dinosaurs were born, lived and died in landscapes that felt familiar. But slowly, over time spans that no single lifetime could perceive, the edges of their worlds moved. Some dinosaurs adapted well to these shifting conditions. Their size, strength, and flexibility allowed them to take advantage of new environments as they formed. Others were more specialized, tied closely to certain types of vegetation or particular climate patterns, and they faced greater challenges as those conditions changed. The growing patchwork of habitats created by drifting continents and changing climates meant that different regions began to favour different kinds of dinosaurs. In wetter, forested areas, large plant eaters with long necks and wide feeding ranges thrived. They could reach high into the canopy for leaves or sweep across low vegetation, using their size to access resources that smaller animals could not. In drier, more open regions, other herbivores evolved body shapes and behaviours suited to grazing on tough, low-growing plants. Some developed strong jaws and specialised teeth for processing fibrous material. Others relied on speed and group behaviour to protect themselves from predators in exposed landscapes. Predatory dinosaurs followed their prey, and in doing so they too began to diverge. In some regions, large, powerful hunters dominated, relying on strength and size to bring down equally large herbivores. In others, smaller, more agile predators were more successful, darting through complex terrain or hunting in coordinated groups. These regional differences grew more pronounced as the continents continued to separate. Fossil evidence from different parts of the world shows that while dinosaurs shared many common traits, the specific species and forms present in one region could be quite different from those in another. What had once been a more unified global community of dinosaurs was becoming a collection of regional lineages, each shaped by the unique conditions of its drifting home. One of the quieter influences on dinosaur life during this period was the changing pattern of plants. As climates divided and ecosystems diversified, the composition of forests and plains shifted. Some regions saw the rise of new plant groups, while others retained older forms of vegetation. This mattered deeply to herbivores. A dinosaur adapted to feeding on one type of plant might struggle in a region where that plant was replaced by another. This created pressure for adaptation, whether through changes in feeding behaviour, tooth structure, or body size. Over long periods, these pressures could lead to the emergence of new species, each better suited to its local plant community. Predators were indirectly shaped by these same forces. Changes in the size, abundance, and behaviour of herbivores influenced how predators hunted, and what kinds of traits were most successful. In a region dominated by large, slow-moving plant eaters, strength and endurance might be favoured. In an area where prey was smaller and faster, agility and keen senses could make the difference between success and failure. The breakup of Pangea, then, did not just divide dinosaur populations geographically, it reshaped the entire web of interactions they were part of, from the plants at the base of the food chain to the top predators at its peak. Another important factor was the rise of natural barriers. As seas widened and mountains grew, some dinosaur populations found themselves effectively cut off from others. A stretch of water too wide to cross or a range too high and cold to traverse could turn a once-connected population into a local one. In these isolated regions, dinosaurs began to follow their own evolutionary paths. Body sizes, shapes, and behaviours drifted in directions that reflected local conditions rather than global trends. In some cases, this led to the development of forms that were quite distinct from their relatives elsewhere. Fossils from later periods show dinosaurs in different parts of the world with unique features that likely evolved in response to regional pressures. This pattern mirrors what happened to many other groups of organisms during this time. Isolation created space for experimentation, and dinosaurs, despite their size and dominance, were not immune to the forces that shape the rest of life. It is also worth noting that the world of the dinosaurs was not just about dinosaurs. Early mammals, birds, insects, and a wide range of reptiles shared the landscape with them. As the continents drifted and climates shifted, these smaller creatures were also adapting, often in ways that would eventually have major consequences. In forested regions, for example, small, agile animals that could climb or burrow found ways to avoid dinosaur predators and exploit food sources that larger animals could not reach. These small creatures were not yet dominant, but they were becoming more diverse and more specialised, quietly preparing for a future that would look very different from the present. The oceans too were part of this story. Marine reptiles, fish and invertebrates were influenced by the opening seas and shifting currents, and coastal dinosaurs interacted with these marine environments in various ways. Some species fed along shorelines, taking advantage of resources washed up by the tides. Others lived in regions where rivers met the sea, moving between freshwater and coastal habitats. These transitional zones became important areas of exchange, where changes in the marine world could influence life on land and vice versa. Another layer of complexity came from the planet's changing seasons. As climates became more regional and less uniform, dinosaurs in different parts of the world experienced different patterns of light, temperature, and rainfall. This influenced when they bred, when they migrated, and how they moved across the landscape. In regions with strong seasonal contrasts, some species may have followed regular migration routes, moving between lowlands and highlands, or between wetter and drier areas as conditions change throughout the year. In more stable climates, year-round residency may have been more common, with animals staying within a relatively small range and developing close ties to specific habitats. These differences in behaviour further contributed to the growing regional character of dinosaur communities. The fossil record hints at this complexity. In some regions, dinosaur species appear to have had wide distributions, suggesting they were able to move across large areas or tolerate a range of conditions. In others, species are found only in narrow geographic zones, indicating more limited ranges and possibly stronger specialization. One of the most striking aspects of this period is how long it lasted. The breakup of Pangea and the age of the dinosaurs overlapped for tens of millions of years. During this time, the world was neither fully united nor fully divided. It existed in a state of transition, with land masses slowly pulling apart and ecosystems constantly adjusting to the changing geography. This extended period of change created both stability and opportunity. Stability, because the overall structure of the world did not shift dramatically within a single lifetime. Opportunity, because the long-term trends opened new habitats and new challenges that could drive evolutionary innovation. Some dinosaur lineages took advantage of these opportunities, spreading into new regions as connections briefly opened or climates shifted in their favour. Others became increasingly tied to specific areas, developing traits that made them highly successful in one place, but less adaptable elsewhere. These patterns meant that the fate of dinosaur species was becoming more closely linked to the fate of the land they lived on. When a region experienced a major change, such as a shift in climate or the loss of a key migration route, the local dinosaur community could be affected in profound ways. In some cases, this led to local extinctions, where species disappeared from one area but continued to exist in others. In other cases, it led to the rise of new species that filled the roles left behind. This regionalization of dinosaur life was a subtle but important step toward the more fragmented world that would come later. The idea of a single, global dinosaur fauna became less accurate as time went on. Instead, different parts of the world developed their own characteristic sets of species, each shaped by local conditions and history. This diversity was, in many ways, a sign of success. Dinosaurs had managed to spread across nearly every part of the drifting continents, adapting to a wide range of environments and lifestyles. They were not just survivors. They were innovators, exploring different ways of living on a changing planet. Yet this same diversity also meant that they were increasingly tied to specific ecological networks. A large herbivore depended on certain types of plants. A predator depended on that herbivore. If a climate shift or geological change disrupted that network, the effects could ripple through the entire system. The more specialized and interconnected a community became, the more sensitive it could be to disruption. This is not to say that dinosaurs were on the brink of collapse during this period. Far from it. For most of this time, they remained the dominant land animals, thriving across a wide range of environments. But the underlying structure of the world they lived in was becoming more complex and more divided. This complexity set the stage for how they would respond to future challenges. As the continents continued to drift, the distances between regions grew larger. ocean barriers became more permanent, climate zones became more established. The paths that dinosaurs could use to move between parts of the world narrowed and, in some cases, closed entirely. This meant that when a major global event eventually occurred, whether related to climate, volcanic activity, or something else entirely, its effects would not be experienced in the same way everywhere. Some regions might be hit harder than others. Some communities might be more resilient, while others might be more vulnerable. The breakup of Pangea had, in a sense, created a world of many separate stages, each with its own cast of characters and its own balance of relationships. Dinosaurs were the stars of many of these stages, but they were not performing the same play everywhere. In one region, massive long-necked herbivores might dominate wide floodplains. In another, smaller armoured forms might browse in drier, more rugged terrain. In coastal areas, mixed communities might take advantage of both land and marine resources. Predators, too, varied in size and style, reflecting the prey and landscapes of their home regions. This variation made the world richer and more interesting, but it also meant that there was no single, unified dinosaur story anymore. There were many stories unfolding in parallel across the drifting continents. From a deep time perspective, this period can be seen as both a high point and a turning point. A high point because dinosaurs had achieved an extraordinary level of global success and diversity. They occupied nearly every terrestrial niche available to large animals, and they did so for a very long time. A turning point because the world they dominated was becoming increasingly fragmented and complex, laying the groundwork for changes that would eventually alter the balance of life on Earth. For the smaller creatures living in the margins of this dinosaur world, this complexity created opportunities. As large animals became tied to specific habitats and regions, smaller, more flexible animals could exploit the spaces in between. They could move through dense vegetation, burrow into the ground, or take to the air, navigating the increasingly varied landscapes in ways that larger animals could not. These small advantages multiplied over time would become important later. For now, though, the world remained very much a dinosaur's world. The sun still rose over landscapes shaped by their footprints. Rivers still flowed past their feeding grounds. Forests still grew and fell under their influence. But beneath all of this, the slow movement of continents and the quiet reshaping of climates continued. The great reptiles were living on a planet that was, in its own patient way, preparing for the next major shift in its long story. As the land continued to drift and the seas continued to widen, the next changes would not only affect who lived where, but also who survived at all. The path ahead would lead through periods of loss and renewal, where extinction and opportunity would walk side by side, reshaping the living world in ways that would echo far beyond the age of dinosaurs and into the world we recognise today. Across the widening face of the planet, the living world began to arrange itself into pockets that felt, in their own quiet way, complete. These were places where the flow of animals, plants and even weather patterns slowed or stopped at natural boundaries, and within those boundaries life started to follow its own internal logic. The land no longer offered a single, shared backdrop. It offered a collection of separate stages, each shaped by a particular mix of geography, climate, and chance. In these emerging regions, what lived there depended less on what existed elsewhere, and more on what could survive and thrive locally. A forest along a newly formed coastline might develop in a way that had little resemblance to a forest on a distant drifting landmass, even if the two once shared the same roots in the ancient world of Pangea. This was the beginning of what we now recognise as isolated ecosystems. Isolation did not always mean complete separation by water. Often, it was created by a combination of factors that worked together to limit movement. A mountain range might block moist air and create a dry zone that few forest species could cross. A wide open plain might be too exposed for animals adapted to dense cover. A stretch of cold, stormy sea might be impassable for creatures that could not swim or fly. These barriers shape the boundaries of ecosystems in much the same way that walls shape the rooms of a building. Inside each room, life arranged itself according to the resources available, the competitors present, and the challenges imposed by the local environment. One of the first things to become noticeable in these isolated systems was how quickly they developed their own internal balance. In a region with a stable climate and predictable resources, populations could grow until they reached the limits of what the land and water could support. Predators and prey settled into relationships that, while never perfectly stable, tended to follow familiar patterns over long periods. In more variable regions where droughts, floods, or temperature swings were common, the balance was more fragile. Populations rose and fell more dramatically, and the composition of the ecosystem could change noticeably within a few generations. These differences influenced how resilient each system was to change. A stable, diverse ecosystem might absorb a disturbance and recover, while a simpler, more tightly constrained one might be pushed into a completely new state by the same event. The shape of the land played a major role in determining how these systems formed. In areas where the terrain was complex with hills, valleys, rivers and varied soil types, many small habitats could exist close together. This allowed a wide range of species to coexist, each occupying a slightly different niche. In flatter, more uniform regions, fewer distinct habitats were available. Species in these areas often had broader ranges and more generalized lifestyles, moving across large areas in search of food and shelter. As continents drifted and landscapes became more varied, the number of these small distinct habitats increased. This, in turn, encouraged the development of more specialized forms of life. Plants were often the foundation of this process. In a newly isolated region, the types of plants that managed to establish themselves first had a powerful influence on everything that followed. They shaped the soil by adding organic matter, changing its chemistry, and stabilizing or loosening its structure. A forest of tall, deep-rooted trees created a shaded, humid environment beneath its canopy, favoring shade-tolerant plants, insects, and animals. An open landscape dominated by grasses and low shrubs created a sunnier, drier environment, favoring different kinds of species. Once these plant communities took hold, they tended to reinforce their own presence. The conditions they created made it easier for similar plants to grow and harder for very different ones to take over. Animals adapted to these plant communities, and their behavior in turn influenced the plants. Grazers could keep certain species in check, preventing them from becoming too dominant. Burrowing animals could mix the soil, affecting how water and nutrients moved through it. This feedback between plants and animals gave each isolated ecosystem a kind of personality, a set of characteristics that made it distinct from others. Over time, these personalities became more pronounced. In a warm coastal region with steady rainfall, an ecosystem might become dense and layered, with multiple levels of vegetation and a wide variety of insects, birds, and small mammals. Food chains in such a system could be complex, with many species occupying similar roles but using slightly different resources. In a dry inland basin, the ecosystem might be simpler and more streamlined. Fewer plant species, fewer herbivores, and a smaller number of predators might dominate, each adapted to make the most of limited resources. The differences between these systems were not just about which species lived there, but how energy moved through the system. In a lush environment, energy flowed through many pathways. Plants captured sunlight and converted it into growth, which fed a wide range of herbivores, which in turn supported multiple levels of predators and scavengers. In a harsher environment, energy pathways were fewer and more direct. A limited number of plant species supported a limited number of herbivores, and the predator community was often smaller and more specialized. These structural differences affected how ecosystems responded to change. A system with many overlapping pathways could often reroute energy when one species declined. A simpler system might collapse or transform more easily if a key species was lost. The oceans experienced similar patterns of isolation and differentiation. As new basins formed and currents established stable routes, certain regions of the sea became more connected to some areas than to others. A current might carry warm, nutrient-rich water along one coastline, supporting a thriving marine community, while leaving another coastline bathed in colder, less productive water. Reefs, seagrass beds, and coastal wetlands became focal points for marine life, creating dense, localized ecosystems with high levels of diversity. Beyond these areas, in deeper or colder waters, communities were often sparser and more specialized. The shape of the seafloor also contributed to this patchwork. Underwater ridges, trenches, and plateaus guided the flow of deep currents, creating pockets of water with distinct temperature and nutrient profiles. Marine organisms adapted to these conditions, leading to the development of regional marine ecosystems that mirrored the growing diversity on land. One of the most striking features of these isolated systems was how they could produce unique forms of life that were found nowhere else. In a region that remained cut off for long periods, species evolved without outside competition or influence. This allowed them to explore unusual strategies and body plans that might not have succeeded in a more connected world. Some animals developed exaggerated features such as larger horns, thicker armor, or more elaborate displays. Others became highly efficient at exploiting very specific resources, such as a particular type of plant or prey. These unique forms were not necessarily better in a general sense. They were better in their own small worlds, perfectly suited to the conditions and relationships found there. The same was true for plants. Isolated regions often gave rise to species with unusual shapes, growth patterns, or reproductive strategies, reflecting the particular challenges of their environment. These distinctive communities added to the overall richness of life on the planet, even as they increased the differences between regions. Chance events could have outsized effects in these systems. A storm that carried a few seeds across a barrier, a group of animals that managed to cross a narrow land bridge before it disappeared, or a shift in current that brought new larvae to a coastline could introduce new species into an isolated ecosystem. Sometimes these newcomers failed to establish themselves. The existing community might outcompete them, or the conditions might simply be unsuitable. Other times they thrived, reshaping the ecosystem in the process. An introduced plant might alter the structure of the vegetation, changing how light and water were distributed. A new predator might reduce the numbers of a dominant herbivore, allowing certain plants to spread. These changes could ripple through the system, affecting species that had no direct interaction with the newcomer. This made the history of each isolated ecosystem a kind of layered story, built from both long-term trends and sudden, unpredictable events. The movement of the continents ensured that no ecosystem remained truly permanent. A region that was once isolated might later reconnect to others as sea levels fell or land masses shifted. When that happened, species from different systems came into contact, sometimes for the first time in millions of years. These meetings could be peaceful, with species simply adding to the diversity of the region. They could also be disruptive, with competition, predation, and disease reshaping the community. Some species that had thrived in isolation struggled to compete in a more crowded, connected world. Others proved highly successful, spreading into new areas and becoming dominant. This cycle of isolation and reconnection added another layer of complexity to the evolutionary process. It allowed lineages to develop in relative privacy, and then tested their success against a wider pool of competitors. In this way, the drifting continents created a kind of evolutionary workshop, where ideas could be developed locally and then shared, or discarded on a broader stage. The physical environment itself was part of this process. Rivers changed course as land rose or sank, sometimes cutting off a region from fresh water or opening new pathways through the landscape. Coastlines advanced and retreated with changing sea levels, altering the size and shape of coastal ecosystems. Volcanic activity could create new land, wiping out existing communities in one place while providing fresh ground for colonization in another. Each of these changes acted as a reset or a filter, selecting which species could persist and which would be replaced. Over millions of years, this constant reshaping led to ecosystems that were not just collections of species, but products of long intertwined histories. A forest in one region might be dominated by plants that had survived repeated periods of drought and flood. The animals living there might carry traits that reflect generations of dealing with unstable conditions. Another forest, in a more stable climate, might be home to species that had evolved under relatively predictable patterns of light and rain, leading to different strategies for growth and reproduction. These differences were not always obvious at a glance, but they were deeply embedded in the biology of the organisms involved. One of the quieter outcomes of this process was the development of strong ecological relationships within each isolated system. In a region where the same set of species interacted over long periods, those interactions could become finely tuned. A predator might specialize in hunting a particular prey species, while that prey evolved specific defenses in response. A plant might rely on a particular animal for pollination or seed dispersal, and that animal might depend on that plant as a primary food source. These close relationships could make an ecosystem more efficient, but they could also make it more vulnerable. If one key species were lost, the effects could spread quickly through the system. This kind of vulnerability became more common as ecosystems became more isolated and specialized. In contrast, more connected systems, where species from different regions mixed, often had a greater degree of redundancy. If one species declined, another might fill a similar role. The balance between efficiency and resilience became another defining feature of the living world during this era. From a broader perspective, the birth of isolated ecosystems marked a shift in how life was organized on the planet. Instead of a largely continuous web, the living world became a network of semi-independent systems, each linked to the others by occasional connections, but largely shaped by its own internal dynamics. This did not mean that the planet lost its sense of unity. The same sun shone on all these regions, the same atmosphere and oceans connected them in subtle ways. But the day-to-day experience of life in one place could be very different from that in another. This growing diversity of ecological worlds set the stage for future developments. As time went on, some of these isolated systems would become the cradles of major new groups of organisms. Others would preserve older lineages that might disappear elsewhere. The distribution of a life across the planet would increasingly reflect this history of separation and local adaptation. Between the steady rhythms of growth and adaptation, there were moments when the living world seemed to hold its breath. Not in a dramatic pause, not in a single, world-shaking instant, but in stretches of time when conditions grew harder, resources grew thinner, and the balance that had supported whole communities began to wobble. These were the periods when survival became less about thriving and more about simply enduring. The breakup of Pangea did not unfold as a smooth, gentle process. It came with pulses of change, some slow and almost imperceptible, others more abrupt on a geological scale. Volcanic regions flared to life, releasing gases and ash into the air. Ocean currents shifted as new seaways opened or closed. Climate patterns swung between warmer and cooler, wetter and drier, sometimes over spans of time short enough to challenge even adaptable species. In these moments, extinction became a quiet companion to evolution. It did not always arrive as a sudden dramatic event. More often, it came as a gradual thinning. A plant species might fail to produce enough seeds during a series of dry years. An animal population might decline as its preferred food source became scarce. Over generations, numbers dropped, ranges shrank, and eventually a lineage that had once been part of the living world simply faded from the record. These losses were not evenly distributed. Some regions were hit harder than others, depending on how stable their climates and ecosystems were. Isolated systems in particular were vulnerable. A small specialised ecosystem might rely on a narrow set of conditions to function. If those conditions shifted beyond a certain point, there was little room to adjust. A wetland that dried out could lose the plants that anchored its soil and fed its animals. A forest that became too cold or too hot could see its dominant tree species decline, opening the canopy and altering the entire structure of the ecosystem. When a key species disappeared, the effects often rippled outward. Herbivores that depended on a particular plant struggled. Predators that hunted those herbivores faced their own shortages. Scavengers and decomposers were affected in turn. What had once been a stable web of interactions became a network of gaps. In larger, more connected regions, the story could be different. There, species might shift their ranges, moving toward areas where conditions were still favourable. A plant might spread along a river corridor. An animal might follow a changing climate zone across a broad plain. These movements did not prevent extinction entirely, but they offered a form of resilience. Populations that could move or adapt had a better chance of surviving periods of stress. This uneven pattern of loss and survival shaped the living world in subtle ways. Over time, regions that experienced frequent or intense environmental changes tended to lose more species, but they also became places where new forms of life could arise. The removal of dominant species opened space and resources for others to expand or evolve. In this sense, extinction and opportunity were closely linked. Consider a forest where a particular type of tree had long dominated the canopy. If a shift in climate or a disease caused that tree to decline, sunlight would suddenly reach the forest floor. Plants that had once struggled in the shade could grow rapidly, changing the composition of the vegetation. Herbivores that fed on those new plants might increase in number, attracting different predators. Over time, the entire structure of the ecosystem could transform. These kinds of changes did not require a global catastrophe. They could unfold region by region, driven by local conditions and events. Volcanic activity was one of the more powerful forces in this process. Large eruptions released enormous amounts of ash and gas into the atmosphere. Ash could block sunlight, cooling the surface for years at a time. Gases like sulfur dioxide and carbon dioxide could alter the chemistry of the air and the balance of heat trapped near the planet's surface. In regions close to volcanic centres, lava flows could wipe out existing ecosystems, covering the land in fresh rock. At first, these areas were lifeless, bare and exposed, but over time they became places of renewal. Wind and water brought in dust and seeds. Lichens and simple plants took hold, breaking down the rock and creating the first thin layers of soil. More complex plants followed, and with them, insects, small animals, and eventually larger ones. These newly formed landscapes often developed ecosystems that were different from those that had existed before, shaped by the particular sequence of species that arrived and the conditions they encountered. The oceans, too, experienced their own cycles of loss and renewal. Changes in currents and water chemistry could affect plankton populations, which formed the base of marine food webs. A decline in plankton could ripple upward, reducing the numbers of fish, marine reptiles, and other predators. In some periods, parts of the ocean became low in oxygen, creating dead zones where few organisms could survive. These zones could expand or contract depending on climate and circulation patterns, altering the distribution of marine life. Yet even in these challenging conditions, some organisms found ways to persist. Certain bacteria and simple animals could tolerate low oxygen levels. When conditions improved, these survivors became the foundation for the rebuilding of more complex communities. On land, the quieter form of survival often went unnoticed in the grand story of large animals and dramatic landscapes. Small, flexible species tended to fare better during times of stress. Insects, small reptiles, and early mammals could hide in burrows, find shelter in dense vegetation, or survive on a wide range of food sources. These traits allowed them to ride out periods that might be disastrous for larger, more specialized animals. In a drying climate, for example, a large herbivore that depended on a particular type of plant might struggle to find enough food. A small mammal that could eat seeds, insects and roots might manage to get by. This difference in strategy did not make small animals more important at the time, but it did give them a kind of long-term advantage. They became the quiet survivors, the lineages that persisted through multiple cycles of change, ready to expand when conditions allowed. Plants showed similar patterns. Species that produced large numbers of seeds, or seeds that could remain dormant for long periods, were often more resilient to environmental swings. When conditions became favourable again, they could quickly recolonize an area. Plants that relied on more specific conditions for reproduction or growth were more vulnerable. If those conditions disappeared for too long, so did the plants. Over millions of years, these patterns influenced which types of plants became widespread, and which remained confined to particular regions. Another factor in this long dance between extinction and survival was the role of competition. When environments became harsher, competition for limited resources intensified. Species that could use those resources more efficiently, or that could switch to alternative food sources, had an edge. In some cases, this led to the replacement of one species by another that filled a similar role but with slightly different traits. These replacements did not always involve close relatives. A decline in one group of herbivores might open space for a different kind of plant eater to take its place, even if their evolutionary histories were quite separate. This process contributed to the reshaping of ecosystems, sometimes in ways that were not obvious from the fossil record alone. Migration also played a role in survival. As climates shifted, some species were able to track the conditions they preferred by moving across the landscape. This might mean moving toward higher elevations as temperatures rose, or toward lower latitudes as regions cooled. Rivers, coastlines, and mountain passes became important corridors for these movements. In a world of drifting continents, however, these corridors were not always stable. A land bridge that existed for a few million years might disappear beneath rising seas. A river that once flowed in one direction might be diverted by uplift or erosion. Species that depended on these pathways sometimes found themselves stranded when the route closed, cut off from more favourable environments. This added an element of unpredictability to survival. Success did not depend solely on being well adapted to current conditions. It also depended on being in the right place when opportunities to move or expand appeared. The record of this era is full of lineages that rose, spread, and then vanished, leaving behind only traces in the rocks. But it is also full of lineages that persisted quietly, sometimes without much apparent change, through long periods of upheaval. These quiet survivors often lived in places that buffered them from extreme conditions. Coastal regions, for example, tended to experience more moderate climates, thanks to the stabilizing influence of the ocean. Forests with layered canopies could create microclimates beneath them, offering shelter from heat, cold, and wind. Underground environments provided another form of refuge. Burrowing animals could escape surface conditions, finding stable temperatures and protection from predators and storms. Even small patches of suitable habitat could act as lifeboats for species during difficult times. When conditions improved, these refuges became sources of recolonization, allowing species to spread back into areas they had once vacated. This pattern of contraction and expansion shaped the distribution of life across the drifting continents. It also influenced the genetic makeup of surviving populations. Bottlenecks, periods when a population shrank to a small number of individuals, could reduce genetic diversity. When the population later expanded, it did so from a limited genetic pool. This could make the group more uniform, but it could also make it more vulnerable to future challenges. At the same time, it could allow certain traits to become common, even if they were rare before the bottleneck. These genetic shifts added another layer to the long-term effects of extinction and survival. From a broader perspective, it is important to recognize that extinction during this period was not a single, global event. There were times when losses were more widespread and times when they were more localized. There were regions that experienced relative stability for long stretches, and others that went through repeated cycles of disruption and renewal. The result was a living world that was constantly being reshaped, not by one dramatic turning point, but by a continuous interplay of loss and opportunity. This interplay is part of what gives life on Earth its resilience. While individual species and even entire groups can disappear, the overall system has a remarkable capacity to reorganize itself. New forms arise, new relationships form, and ecosystems settle into new patterns. The breakup of Pangea provided a powerful backdrop for this process by creating many separate arenas in which it could play out. Each isolated ecosystem had its own history of stress and recovery, its own mix of survivors and newcomers. Some regions became hotspots of innovation, where new lineages emerged and diversified. Others became museums of older forms, preserving species that had vanished elsewhere. This unevenness is still reflected in the modern world, where certain areas are known for their unique and ancient lineages, while others are centres of rapid diversification. One of the quieter but significant outcomes of this long period of change was the way it prepared the living world for future transformations. By favouring flexibility, resilience, and the ability to survive in small protected populations, these cycles of extinction and survival helped shape lineages that could respond to sudden, large-scale events. The small mammals that hid in burrows and fed on a wide range of foods, the plants that could disperse their seeds widely or wait out unfavourable conditions, the insects that could exploit almost any available niche. These groups did not yet dominate the planet, but they were building a kind of evolutionary readiness. In the larger story of life on Earth, this era can be seen as a long training period, one that tested the capacity of organisms to endure, adapt and recover. The world was becoming more complex, more divided and more dynamic. The living things on it were, in their own ways, learning how to navigate that complexity. As the continents continued to drift and the climates continued to shift, these lessons would become increasingly important. In the long shadows cast by towering reptiles and vast ancient landscapes, a different kind of story was unfolding, one that did not announce itself with size, strength or dominance, but with persistence. The world of drifting continents and changing climates was quietly making room for creatures that had once lived on the margins, surviving in small spaces, hidden places, and overlooked corners of the living world. These were the early mammals. For much of the age of dinosaurs, mammals had remained relatively small and unobtrusive. They scurried through undergrowth, burrowed beneath the ground, and crept along branches, often active at night when many large predators were less active. Their lives were shaped by caution, flexibility, and an ability to make use of whatever resources were available. As the land continued to pull apart and ecosystems became more fragmented, these traits began to take on a new significance. The growing patchwork of isolated regions, shifting climates, and changing landscapes created a world full of small, varied opportunities. Where large animals often needed wide, continuous territories and stable food supplies, smaller animals could survive in narrow strips of habitat, pockets of shelter, and environments that change from place to place. Mammals, with their varied diets and adaptable behaviours, were well suited to this kind of world. One of the most important advantages mammals had was their ability to regulate their own body temperature. Unlike reptiles, which rely heavily on external heat sources to warm their bodies, mammals can generate heat internally. This allowed them to remain active in cooler conditions and in environments where temperature fluctuated widely, between day and night or season to season. As continents drifted into different latitudes and climates became more varied, this trait opened up new regions for mammals. Cooler highlands, temperate forests, and even colder areas near the poles became accessible in ways they had not been before. This did not mean mammals suddenly spread everywhere. They still faced competition and predation, and in many regions, large reptiles and dinosaurs remained the dominant land animals. But it did mean that mammals could establish themselves in places that were less hospitable to some of their competitors. Another key factor was diet. Early mammals were often generalists. They ate insects, seeds, fruits, small animals, and plant material, depending on what was available. This flexible approach to feeding made them resilient in the face of environmental change. When a particular food source declined, they could switch to another. When a habitat changed, they could adjust their foraging behaviour. In a world where ecosystems were becoming more localised and less predictable, this flexibility was a powerful asset. As isolated ecosystems formed, each with its own mix of plants and smaller animals, mammals began to adapt to the specific conditions of their home regions. In forested areas, some developed traits that made them better climbers: stronger limbs, grasping hands or feet. An improved balance allowed them to move through branches and reach food sources that were inaccessible to ground-dwelling animals. In open environments, others became better runners or diggers, using speed or burrowing as ways to avoid predators and cope with exposure. In wetter regions, some adapted to life near water, developing features that helped them swim or forage along riverbanks and shorelines. These early experiments did not yet produce the wide variety of mammal forms we see today, but they marked the beginning of a trend toward greater ecological diversity within the group. Behavioural changes accompanied these physical adaptations. Mammals often invested heavily in caring for their young. This meant fewer offspring at a time, but a greater chance that each one would survive. In stable, resource-rich environments, this strategy allowed populations to grow steadily. In more challenging environments, the ability to shelter young in burrows, nests, or dense vegetation offered protection from both predators and harsh weather. This focus on parental care helped mammals establish themselves in regions where conditions might otherwise have been too unpredictable for long-term survival. The fragmentation of the land also played a role in shaping mammal evolution. As populations became isolated on different drifting pieces of the world, they followed their own evolutionary paths. A group of mammals living in a warm coastal region might adapt to a very different set of challenges than a related group living in a cool inland plateau. Over time, these differences accumulated, leading to the emergence of distinct lineages with their own traits and behaviours. Some became better suited to eating tough plant material. Others specialised in hunting insects or small vertebrates. Still others developed features that allowed them to glide, climb, or move efficiently through complex environments. The result was a growing variety of mammal forms, each tied to a particular way of life and a particular part of the drifting world. One of the quieter but important changes during this period was the development of more sophisticated senses. In the dim, sheltered environments where many early mammals lived, sharp hearing and a strong sense of smell were especially valuable. These senses helped them locate food, avoid predators, and navigate complex terrain. Over generations, these abilities became more refined, contributing to the growing adaptability of the group. The structure of mammal teeth also began to diversify. Different shapes and arrangements of teeth allowed mammals to process different kinds of food more efficiently. Sharp, pointed teeth were useful for catching and cutting insects or meat. Broad, flat teeth were better for grinding plant material. This dental diversity made it easier for mammals to specialize in particular diets, reducing competition between different species and allowing them to coexist in the same region. The opening of new coastal environments and river systems created additional opportunities. Wetlands, floodplains, and forested riverbanks were often rich in insects, seeds, and small animals. These areas could support relatively high densities of small, adaptable mammals. The shifting of rivers and coastlines, driven by tectonic movement and changing sea levels, meant that these productive environments appeared and disappeared over time. Mammals that could move quickly into new areas and exploit these resources gained an advantage. The oceans also influenced mammal evolution in more indirect ways. Coastal climates tended to be more moderate, with fewer extreme temperature swings. These conditions could support more stable plant communities, which in turn supported more reliable food sources for animals. In some regions, this stability allowed mammal populations to persist and diversify over long periods. even as conditions elsewhere were more volatile. Another important factor was the way mammals interacted with other groups of animals. In many ecosystems, they shared the landscape with a wide range of reptiles, birds, and insects. Competition for food and shelter was common, but so were more complex relationships. Some mammals fed on insects that damaged plants, indirectly benefiting the vegetation. Others helped disperse seeds by carrying them in their fur or digestive systems. These interactions helped integrate mammals into the broader ecological networks of their regions, making them part of the fabric of each isolated ecosystem. As time went on, the growing diversity of mammals began to show in the fossil record. Different regions preserved evidence of different forms, reflecting the localized nature of their evolution. In one area, small, agile climbers might be common. In another, burrowing forms might dominate. These patterns mirrored the growing differences between ecosystems across the drifting continents. It is important to remember that this period was still very much a transitional one for mammals. They were not yet the dominant land animals. In many places, large reptiles and dinosaurs continued to shape the structure of ecosystems. But mammals were becoming more than just background players. They were exploring new roles, testing new strategies, and establishing a presence that would become increasingly important in the future. One of the most significant outcomes of this process was the development of what might be called ecological readiness. By diversifying into many different forms and lifestyles, mammals were, in effect, spreading their risk. If conditions changed in one region or one type of habitat, some mammal lineages would likely be affected, but others might thrive. This distributed approach to survival made the group as a whole more resilient. In a world shaped by drifting continents, shifting climates, and periodic environmental stress, resilience was a valuable trait. The quiet expansion of mammals also had an influence on the ecosystems they lived in. As they became more abundant and diverse, they began to play a greater role in shaping plant communities and insect populations. Their feeding and movement patterns affected which plants spread and which were kept in check. In turn, this influenced the structure of habitats, creating feedback loops that further shaped the environment. These effects were often subtle, especially compared to the impact of large herbivores or major geological events. But over long periods, they added up. The presence of mammals contributed to the complexity and dynamism of ecosystems, making them more layered and interconnected. The isolation of regions continued to drive divergence within the group. In some drifting land masses, mammal lineages evolved traits that were not seen elsewhere. These unique forms reflected the particular challenges and opportunities of their environments. In more connected regions, where occasional migration or mixing occurred, mammal populations remained more similar to one another, showing less extreme differences. This uneven pattern of change added to the growing mosaic of life across the planet. From a broader perspective, this phase of mammal evolution can be seen as a period of quiet preparation. The group was building a foundation of diversity, adaptability, and ecological integration that would become crucial later. The world was still largely shaped by the presence of dinosaurs and other large reptiles, but the underlying structure of ecosystems was becoming more flexible and complex. Smaller animals, including mammals, were weaving themselves into that structure in ways that would allow them to respond quickly to future changes. The movement of the continents continued, opening new regions and closing others. Climate patterns kept shifting, sometimes gradually, sometimes in noticeable steps. Ecosystems were tested again and again by changes in temperature, rainfall, and geography. Through all of this, mammals persisted. They did not need vast, continuous territories to survive. They did not rely on a single type of food or habitat. They could hide, adapt, and move into the spaces that opened up between larger, more dominant forms of life. This ability to occupy the in-between spaces was one of their greatest strengths. In some regions, mammals became important prey for larger predators, integrating into existing food webs. In others, They took on roles as predators of insects and small vertebrates, influencing the populations of those groups. In still others, they became key agents of seed dispersal, helping shape the distribution of plants across the landscape. Each of these roles tied mammals more closely to the functioning of their ecosystems. As these connections grew, so did the impact of mammals on the living world. By the end of this phase, the planet was home to a wide range of mammal lineages, each adapted to a particular set of conditions and challenges. Some were still small and relatively simple in form. Others showed signs of increasing complexity and specialization. Together, they represented a quiet but significant shift in the balance of life. The world of drifting continents had given them space to breathe, space to change, and space to explore new ways of living. They had not yet stepped fully into the spotlight, but they were no longer confined to the shadows. The stage was being set for a future where the roles of dominant and supporting players would be reshuffled, not by the slow movement of land or the gradual drift of climate alone, but by a more sudden and far-reaching change that would alter the course of life on Earth. For now, though, the story remains one of steady, patient growth, of small creatures finding room to expand in a world that was still in the midst of becoming something new, carrying forward the long branching journey of life across a planet that never quite stands still. Beneath the shifting skies and across the slowly rearranging land, another transformation was unfolding that did not roar or thunder, but quietly reshaped the face of the planet all the same. It happened leaf by leaf, root by root, seed by seed. While animals moved, hunted, and adapted in visible ways, plants were steadily redrawing the living map of Earth, turning bare ground into forests, open plains into fields of green, and coastlines into layered bands of life that followed the rhythms of water and light. The breakup of Pangea created a world where the rules for growing and surviving changed from place to place. New coastlines introduced salt spray and shifting sands. Rising mountains brought cooler air and thinner soils. Expanding deserts challenged anything that depended on steady rainfall. In this patchwork of conditions, plants became the architect of the landscape, shaping not just what the world looked like, but how every other form of life could exist within it. One of the most important shifts during this period was the increasing influence of flowering plants. For much of Earth's earlier history, the land had been dominated by ferns, conifers, and other seed-bearing plants that relied on wind or simple dispersal methods to spread. Flowering plants, also known as angiosperms, introduced a different strategy. They formed partnerships with animals, using insects, and later birds and mammals to carry pollen and seeds from one place to another. This change had far-reaching effects. In regions where insects were abundant, flowering plants could spread quickly and diversify rapidly. Different species developed different shapes, colours, and scents to attract specific pollinators. A plant that relied on one type of insect might evolve a flower that fit that insect's body perfectly, while a nearby plant might develop a completely different form to attract another. As continents drifted and ecosystems became isolated, these relationships often developed independently in different regions. The result was a growing variety of plant forms that reflected local conditions and local partners. In one drifting landmass, tall, broad-leaved trees might dominate, forming dense forests with shaded understories. In another, low-growing shrubs and grasses might spread across open plains, shaped by wind, grazing, and limited water. These differences were not just cosmetic, they influenced how energy moved through the ecosystem. A dense forest captures sunlight in multiple layers, from the canopy to the forest floor. This allows for a complex web of life, with insects, birds, and mammals occupying different levels of the vegetation. An open grassland, by contrast, captures sunlight close to the ground. Energy flows more directly from plants to large grazers, and then to predators, creating a different kind of ecological structure. The drift of continents created new opportunities for both kinds of systems to expand. As regions moved into warmer, wetter climate zones, forests spread. As others became drier or cooler, grasslands and open woodlands took their place. These shifts did not happen in neat, clean lines. They followed the contours of the land, the direction of winds, and the availability of water. Rivers became corridors of green in otherwise dry landscapes. Mountain slopes hosted bands of different vegetation, with dense growth in lower, wetter areas and sparse, hardy plants at higher elevations. Along coastlines, plants adapted to salt, shifting sands, and periodic flooding formed unique communities that looked nothing like those found farther inland. Seeds were the travellers in this story. Carried by wind, water, and animals, they moved across barriers and into new regions whenever conditions allowed. A seed that landed in a suitable place could become the start of a new population, shaping the future of that ecosystem. This process was influenced by chance as much as by design. A storm might carry seeds across a narrow sea. A bird might drop a fruit far from where it was eaten. A river might deposit plant material on a newly formed floodplain. Some of these arrivals failed. The conditions might be wrong, or local plants might outcompete the newcomers. Others succeeded, sometimes with dramatic consequences. A new plant species could alter the structure of the vegetation, changing how much light reached the ground, how water moved through the soil, and which animals could find food and shelter there. These changes could ripple through the ecosystem, affecting species that never interacted directly with the plant itself. Over time, this made plant communities powerful drivers of regional identity. Two regions with similar climates and soils could develop very different ecosystems simply because different plants happened to establish themselves first and shape the environment in their own way. The rise of grasses was one of the most significant developments during this long period of change. Grasses are well suited to open, dry, and frequently disturbed environments. They grow from their base rather than their tips, which allows them to recover quickly from grazing or fire. As some regions of the drifting continents became drier and more seasonal, grasses spread across wide areas, forming vast open landscapes. These grasslands supported large populations of grazing animals, which in turn influenced the evolution of predators and scavengers. The presence of grazers helped maintain the open nature of these environments, preventing trees and shrubs from taking over. This feedback loop between plants and animals created stable, long-lasting ecosystems that would become a defining feature of many parts of the modern world. Forests, meanwhile, continued to dominate in regions with reliable rainfall and moderate temperatures. In these areas, competition for light became a major driver of plant evolution. Trees that could grow taller and faster had an advantage, capturing sunlight before it reached the lower levels. This led to the development of layered forests, with towering canopy trees, smaller understory trees, shrubs and ground-level plants all occupying different niches. These complex structures supported a wide range of animals, from insects and birds to climbing mammals and large herbivores. The interaction between plants and climate became increasingly intricate. Plants influence climate by affecting how much sunlight is absorbed or reflected, how much water is released into the air through transpiration, and how carbon is stored in the soil and vegetation. As plant communities changed, they altered these processes, which in turn influenced local and regional climate patterns. For example, a forested area tends to be cooler and more humid than an open plain, because trees provide shade and release moisture into the air. When a region shifted from forest to grassland or vice versa, it could experience changes in temperature, rainfall, and even wind patterns. These changes fed back into the plant community, reinforcing the new state or sometimes pushing the system toward yet another configuration. In this way, plants and climate were engaged in a continuous conversation, each shaping the other over long periods of time. The oceans played a role in this story as well. Coastal plant communities were influenced by sea levels, tides, and the availability of nutrients carried by rivers and ocean currents. Mangrove-like forests and salt-tolerant plants formed in shallow, sheltered coastal areas, creating environments that supported both marine and terrestrial life. These zones acted as buffers, protecting inland areas from storms and erosion, while providing rich habitats for fish, birds, and small animals. As sea levels rose and fell, these coastal systems expanded and contracted, leaving behind layers of sediment and organic material that would later become fertile ground for new plant communities. In some regions, plants also began to play a more active role in shaping the physical landscape. Roots stabilize soil, reducing erosion, and allowing sediment to build up in place rather than being washed away. In river valleys, dense vegetation slowed the flow of water, encouraging the formation of floodplains and wetlands. On slopes, plants helped anchor loose material, influencing where landslides occurred and how quickly mountains were worn down. These physical effects tied plant evolution directly to the geological processes shaping the continents. The spread of vegetation could alter the course of rivers, the shape of coastlines, and the stability of hillsides, creating a feedback loop between living and non-living systems. As isolated ecosystems developed, plant communities within them became increasingly distinctive. In one region, a particular group of trees might dominate, creating a forest type found nowhere else. In another, a unique mix of shrubs and grasses might define the landscape. These regional differences influenced the evolution of animals that depended on the plants for food and shelter. Herbivores adapted to the specific plants available in their environment. Insects specialized in feeding on certain leaves or flowers. Birds and mammals evolved to take advantage of particular fruits or seeds. This tight coupling between plants and animals made ecosystems more cohesive, but also more sensitive to change. If a key plant species declined, the animals that depended on it could be affected, and those effects could cascade through the system. Fire became an increasingly important factor in some plant communities. In dry seasonal climates, periodic fires cleared old vegetation and released nutrients into the soil. Some plants evolved traits that allowed them to survive or even take advantage of fire. Thick bark, seeds that only germinate after exposure to heat, and rapid regrowth from underground structures became common in fire-prone regions. These adaptations helped shape landscapes where fire was a regular part of the ecological cycle. In such places, the plant community and the fire regime became linked, each influencing the frequency and intensity of the other. This added another layer of regional character to the drifting continents. One area might be dominated by fire-adapted grasslands and open woodlands, while another, with a wetter climate, might support dense fire-resistant forests. These differences further contributed to the growing variety of ecosystems across the planet. The fossil record from this period reflects these changes in striking ways. Pollen grains, leaves, and fossilized wood preserved in sediment layers show shifts in plant communities over time. In some regions, layers of sediment reveal transitions from forested environments to open plains, or from wetland to dryland conditions. These records allow scientists to trace how plant life responded to changing climates, sea levels, and continental positions. They also reveal how quickly plant communities could change in response to new conditions, sometimes within relatively short geological periods. This responsiveness made plants key players in the broader story of life's adaptation to a changing world. Another quiet but important development was the increasing role of plants in regulating the planet's carbon cycle. Through photosynthesis, plants remove carbon dioxide from the atmosphere and store it in their tissues and in the soil. As plant communities expanded or contracted, they influenced how much carbon was held on land versus in the air or oceans. In periods of widespread forest growth, more carbon was stored in vegetation and soils, which could contribute to cooler global temperatures. In periods when forests declined and open landscapes expanded, carbon could be released back into the atmosphere, potentially contributing to warming. These long-term interactions between plants and climate added another layer of complexity to the Earth system. From the perspective of life on the ground, plants were not just background scenery. They were the foundation of nearly every ecosystem. They determined where animals could live, what they could eat, and how they could move. A dense thicket could provide shelter from predators. An open plain could offer wide visibility but little cover. A forest canopy could create a shaded world beneath it, with its own microclimate and set of challenges. As the continents continued to drift, these plant-built worlds became more varied and more localized. A traveller moving from one region to another might pass through a sequence of completely different landscapes, each with its own dominant plants and associated animals. This variety was a direct result of the way plants responded to the changing geography and climate of the planet. They were, in effect, rewriting the green map of Earth one region at a time. The importance of this process becomes even clearer when considering what came later. The structure of modern ecosystems, from tropical rainforests to temperate woodlands and vast grasslands, has its roots in these ancient shifts in plant life. The distribution of many animal groups today still reflects the plant communities that shaped their ancestors' worlds. Looking across the planet as it slowly took on the familiar outlines we recognise today, it becomes clear that what we call the modern world is not something that simply appeared. It is the result of a long chain of movements, separations and reconnections that began when a single landmass started to come apart. The mountains, oceans, forests, deserts and coastlines that define life now are all echoes of that ancient process, shaped by the quiet persistence of drifting continents and the living systems that grew up around them. By the time the major pieces of Pangea had moved far enough apart to feel like distinct worlds, each carried with it a history written into its rocks, soils and living communities. These histories did not stay separate. They continued to interact, sometimes gently, sometimes with great force, as the planet kept changing. Consider the way the oceans now lie between the continents. The Atlantic, once a narrow seam of water between separating plates, grew into a vast basin that reshaped climate on both sides. Warm currents flowing northward helped create the mild, wet conditions of Western Europe, while colder currents influenced the climates of eastern North America and parts of Africa. These flows affected where forests could grow, where ice might form, and where life found its most stable footholds. The Pacific, shrinking as plates continued to converge around its edges, became a region of intense geological activity. Earthquakes, volcanoes, and rising mountain chains around its margins shaped coastlines and ecosystems in ways that are still unfolding today. The Indian Ocean, formed as land masses like Africa, India, and Australia moved apart, created new pathways for heat and moisture, influencing monsoon systems and the distribution of rainfall across large parts of the world. These bodies of water are not just gaps between continents. They are active participants in shaping the planet, moving heat, nutrients, and life itself across enormous distances. The continents themselves carry the marks of their shared origin. Look at the way coastlines on opposite sides of the Atlantic seem to fit together, like pieces of a puzzle. This is more than a visual coincidence. The rocks on one side often match those on the other, telling a story of mountains and plains that were once continuous. The Appalachian Mountains in North America and the Caledonian Ranges in Europe and parts of Africa share a common ancestry, formed when ancient landmasses collided long before Pangea even existed. Their separation and continued erosion reveal how the same geological features can be shaped into different landscapes when placed in different climates and environments. The Himalayas, towering and young by geological standards, are another reminder that the story of moving continents did not end with the breakup of Pangea. India's journey northward and its collision with Asia created one of the most dramatic examples of how drifting land can reshape the surface of the planet. This ongoing motion means that the world we inherited is not finished. It is still being written, one slow movement at a time. The distribution of life across the planet reflects this long history of separation and connection. Why do marsupials dominate in Australia but are rare elsewhere? Why do certain plant families appear only in specific regions, even when climates are similar? Why do some islands host species found nowhere else on Earth? These patterns make sense when seen as the legacy of drifting continents and isolated ecosystems. Australia, once part of a larger southern landmass, broke away and remained isolated for tens of millions of years. During that time, its mammals followed evolutionary paths that were largely cut off from the rest of the world. When placental mammals spread across other continents, Australia's marsupials continued to diversify in relative isolation, filling many of the same ecological roles in their own unique ways. South America experienced a similar period of isolation after it separated from Africa. Its mammal communities developed along their own lines, with distinctive groups of predators and herbivores. When it later reconnected with North America, a wave of migration reshaped ecosystems on both continents, blending lineages that had evolved separately for millions of years. These events show how the timing and sequence of connections between landmasses can have lasting effects on the living world. Plants tell similar stories. The distribution of certain tree families across southern continents points back to a time when those lands were joined in a supercontinent often called Gondwana, this southern portion of Pangea. Even today, related species can be found in South America, Africa, Australia and Antarctica, separated by vast oceans but connected by a shared ancestry. The climates of these regions have diverged dramatically since then, and the plants have adapted in different ways. Some now thrive in tropical rainforests, others in temperate woodlands or dry scrublands. Yet their underlying relationships reveal the deep history of a world that was once whole. The influence of the broken supercontinent extends beyond biology into the very shape of the land. River systems often follow ancient geological lines, tracing paths that were set long before the continents reached their current positions. Sediment carried by these rivers builds deltas and plains that support some of the most fertile and densely populated regions on Earth today. The Nile, the Amazon, the Mississippi, and countless other rivers are part of a global network shaped by the rise and fall of land, the opening and closing of seas, and the slow tilting of continents. Even the location of many natural resources is tied to this deep history. Coal deposits, formed from ancient forests and wetlands, often appear in regions that were once part of the same climatic belts on Pangea. Oil and gas reserves are linked to the accumulation of organic material in ancient seas that formed as continents pulled apart and new basins developed. Metal ores can be associated with volcanic activity and mountain-building events that occurred during periods of tectonic movement. These resources have played major roles in human history, influencing where cities were built, how economies developed, and even how conflicts arose. In this way, the breakup of a supercontinent continues to shape not just the natural world, but human societies as well. The climates we experience today are also part of this inheritance. The arrangement of continents and oceans determines how heat is distributed across the planet. The presence of large land masses near the poles, for example, makes it easier for ice to form and persist, influencing global climate patterns. The shape of ocean basins guides major currents like the Gulf Stream, which carries warm water northward and helps keep parts of Europe much milder than they would otherwise be at that latitude. Monsoon systems in Asia and Africa are influenced by the way land and sea are arranged, creating seasonal patterns of rainfall that support hundreds of millions of people. These systems did not arise by chance. They are the result of millions of years of tectonic movement, reshaping the boundaries between land and water. The idea of a natural world separate from human influence becomes more complex when seen through this lens. The landscapes we walk through, the climates we live under, and the ecosystems we depend on are all products of processes that began long before our species existed. At the same time, humans are now part of that ongoing story, influencing the planet in ways that can rival some of the natural forces that shaped it in the past. Understanding the deep history of the world can provide perspective on this role. When we see a forest, a desert, or a coastline as the result of millions of years of change, it becomes easier to recognize how delicate and interconnected these systems are. The fragmentation of Pangea led to a world of extraordinary diversity. Different regions developed their own climates, landscapes, and living communities. This diversity is one of the defining features of the planet today. Tropical rainforests teem with life, hosting more species in a single hectare than some entire regions elsewhere. Deserts, though seemingly barren, support highly specialized organisms adapted to extreme conditions. Polar regions, cold and sparse, still harbor unique ecosystems shaped by long periods of isolation and harsh climates. These contrasts exist because the land and sea were rearranged in ways that created a wide range of environments. At the same time, there are underlying similarities that hint at a shared origin. The basic structure of ecosystems, with plants capturing energy from the sun, herbivores feeding on plants and predators feeding on herbivores, is found almost everywhere. The same chemical elements, the same biological building blocks, and the same fundamental processes of growth, reproduction, and adaptation operate across the globe. This combination of unity and diversity reflects the history of a world that was once one and is now many. There is also a sense of motion embedded in the landscapes we see. Mountains that appear solid and immovable are, in geological terms, temporary features. They rise, erode, and eventually disappear, only to be replaced by new ranges formed by later movements of the crust. Coastlines shift as sea levels rise and fall. Rivers change course. Islands appear and vanish. The continents themselves continue to drift, though so slowly that the movement is invisible in a human lifetime. Africa is gradually splitting along a great rift, which may one day become a new ocean. Australia is moving northward toward Asia. The Americas are drifting westward. The Pacific is shrinking as its crust is recycled into the mantle along its edges. These changes mean that the world we inherited is not the world that will exist in the far future. Just as Pangea came together and then broke apart, the current arrangement of continents is likely to change, perhaps forming a new supercontinent millions of years from now. Life will respond to those changes just as it has in the past, adapting, diversifying, and finding new ways to survive. The patterns we see today in the distribution of species offer hints about how that future might unfold. Regions that are isolated now may one day reconnect, allowing lineages that have evolved separately to meet and interact. New barriers may form, creating fresh opportunities for divergence. Climate zones may shift as land masses move into different latitudes, or as ocean currents change their paths. The long story of a changing planet continues. From a human perspective, it is easy to feel small in the face of these vast timescales. Our lives span decades. The breakup of Pangea unfolded over hundreds of millions of years. The continents we see today will continue to move long after our species is gone. Yet we are part of this story, connected to it in ways that are both practical and profound. The food we eat, the water we drink, and the air we breathe all come from systems shaped by this deep history. The soils that grow our crops were formed from rocks uplifted, eroded, and deposited through countless cycles of geological change. The climate that supports agriculture is influenced by the arrangement of land and sea that began when a supercontinent started to break apart. Even the cultural and economic patterns of human societies often follow the contours of the natural world, clustering along rivers, coasts, and fertile plains shaped by ancient processes. There is a kind of quiet continuity in this. The same forces that guided the movement of continents and the evolution of life also shape the conditions under which we live. Understanding this continuity can change the way we see the world around us. A mountain range is not just a backdrop. It is the result of plates colliding or pulling apart, of rocks rising and wearing down over immense spans of time. A forest is not just a collection of trees. It is part of a long lineage of plant communities that spread, retreated, and adapted as climates and landscapes changed. An ocean is not just a body of water. It is a dynamic system that connects distant parts of the planet, carrying heat, nutrients, and life along paths established by the shape of the seafloor and the position of the continents. The world we inherited from a broken supercontinent is, in this sense, a layered world. Each layer represents a different chapter of its history, from ancient collisions and separations to the rise of mountains, the opening of seas, and the branching of life into countless forms. These layers are not always visible, but they are always present, shaping the conditions of the present. As we move forward in this story, it is worth keeping in mind that what feels stable and permanent is often just a moment in a much longer sequence. The forests, plains, and cities of today exist within a framework that is still shifting. The continents are still moving, the climate is still changing, life is still evolving. The legacy of Pangea is not just found in the shapes of the continents or the distribution of species. It is found in the idea that the planet is always in the process of becoming something new. Even now, as the outlines of the continents feel familiar and the maps of the world seem settled, the ground beneath everything is still in motion. It moves so slowly that no human lifetime can measure it directly, yet that movement is constant, patient, and unstoppable. The planet that once held all its land in a single unbroken mass has never truly stopped rearranging itself. What we see today is not an ending, but a moment in a much longer sequence. The story of drifting land did not conclude when Pangea broke apart into the shapes we recognize. It simply entered a new phase, one defined by quieter shifts that continued to shape climates, landscapes, and living communities in ways that will become more obvious over the deep future. Take the continents themselves. Africa is gradually pulling away from itself along a great line of fractures that stretches from the Red Sea down through eastern Africa. Over millions of years, this rift has been widening, creating valleys, lakes, and volcanic regions. The land on either side is slowly drifting apart. If this process continues, a new ocean basin will eventually form, splitting a piece of the continent into its own drifting landmass. Australia is moving northward, inching closer to Southeast Asia. This slow approach is already influencing the distribution of plants and animals. Species that once evolved in isolation on the Australian landmass are beginning to encounter relatives from Asia, creating new opportunities for mixing, competition, and change. The Americas continue to move westward, driven by the slow push of spreading ridges in the Atlantic. Along their western edges, plates dive beneath one another, fueling earthquakes, volcanoes, and the steady rise of mountain chains like the Andes and the ranges of western North America. The Pacific Ocean, once larger than it is today, is slowly shrinking as its crust is recycled back into the Earth's interior along its margins. In the far future, this vast basin may close entirely, replaced by a new supercontinent that brings today's distant lands back together in unfamiliar arrangements. These movements are not just geological curiosities, they influence how the planet functions as a living system. As continents shift, they change the shape of ocean basins. This alters the paths of major currents that move heat around the globe. A slight change in the course of a warm current can mean the difference between a mild, wet climate and a cold, dry one for an entire region. The rise of a mountain range can block moist air, creating rain shadows and turning once green landscapes into dry plains or deserts. The opening of a new seaway can allow water from different parts of the ocean to mix, affecting temperatures, nutrient flows, and the distribution of marine life. In this way, the movement of the land continues to shape the living world, just as it did during the breakup of Pangea. Life, in turn, continues to respond. Species shift their ranges as climates change. Plants spread into new areas when conditions allow. Animals follow food sources, water, and suitable temperatures across the landscape. Some of these movements happen quickly, over generations or even within a single lifetime. Others unfold over thousands of years, barely noticeable until viewed from a long-term perspective. The modern world offers many examples of this ongoing process. As temperatures rise in certain regions, plant communities move uphill or toward the poles. Insects and birds expand their ranges into areas that were once too cold for them. Marine species follow changing ocean temperatures, altering the composition of coastal ecosystems. These shifts echo the ancient patterns set in motion when continents first began to drift apart. The idea of a stable, unchanging natural world is, in this light, more of an illusion than a reality. Stability exists, but it is always temporary, held in place by a balance of forces that are themselves in motion. Ecosystems that seem timeless, such as old-growth forests or long-established coral reefs, are the result of long periods of relative consistency. But even these systems can change when conditions cross certain thresholds. A prolonged drought, a series of powerful storms, or a shift in ocean chemistry can alter them in ways that take centuries or millennia to reverse. The deep history of the planet suggests that change is not the exception, it is the rule. What makes the present moment different is the growing influence of a single species. Humans now shape the planet in ways that can rival some of the natural processes that once dominated its story. We move vast amounts of rock and soil, alter the flow of rivers, clear forests, and change the composition of the atmosphere. These actions interact with the ongoing movement of continents and the natural rhythms of climate and life, adding a new layer of complexity to the system. From a long-term perspective, this makes the present era part of the same unfolding narrative rather than a break from it. Just as the breakup of Pangea reshaped the world in ways that life had to respond to, the changes happening now are creating new conditions that will influence the future paths of ecosystems and species. Some lineages will adapt, others will decline. New relationships will form, and new patterns of distribution will emerge. The details will be different, but the underlying process is familiar. Looking ahead, scientists can imagine several possible futures for the planet's geography. One scenario involves the continued closure of the Pacific and the formation of a new supercontinent as the Americas collide with Asia. Another envisions Africa pushing into Europe, closing the Mediterranean and raising new mountain ranges. Yet another suggests that the Atlantic might eventually begin to shrink as new subduction zones form along its edges. Each of these outcomes would reshape the planet in dramatic ways. Ocean currents would be rerouted, climate zones would shift, entire regions would become wetter, drier, warmer or colder. Life would respond just as it has in the past, spreading into new areas, retreating from others, and evolving in response to the new patterns of land and sea. These future worlds will not look like the present one, just as the present world does not look like the time of Pangea. The continuity lies in the process, not in the outcome. The story of a drifting planet is, at its core, a story about connection and separation. Land comes together and pulls apart. Populations mix and then become isolated. Climates link distant regions through shared currents and wind patterns, even as local conditions create distinct environments. This interplay has been shaping life for hundreds of millions of years, and it shows no sign of stopping. One of the most striking lessons of this long history is how small changes can lead to large effects over time. A narrow seaway opening between two landmasses can eventually become a major ocean basin. A slight shift in latitude can turn a lush region into a dry one. A new mountain range can alter rainfall patterns across an entire continent. These physical changes create new challenges and opportunities for living things, guiding the direction of evolution in ways that only become clear over deep time. The living world, for its part, is both resilient and fragile. It has survived mass extinctions, climate swings, and the rearrangement of the continents themselves. Yet it can also be sensitive to disruptions, especially when systems become highly specialized or tightly interconnected. The balance between these two qualities is part of what gives the planet its dynamic character. In the long view, extinction and creation are not opposites. They are linked parts of a continuous process of change. Lineages disappear, leaving space for others to expand or emerge. Ecosystems transform, opening new niches and closing old ones. This does not make loss any less real for the organisms involved, but it places it within a broader context of ongoing transformation. From a human standpoint, engaging with this deep time perspective can shift the way we think about our place in the world. The landscapes we inhabit are not static backdrops. They are chapters in a much longer story that began long before our species existed and will continue long after. The coastlines we walk along were once parts of ancient mountain ranges or the floors of vanished seas. The mountains we climb were once sediments at the bottom of oceans. The forests we move through are descendants of plant communities that spread and retreated as continents drifted and climates changed. Even the air we breathe has been shaped by the long interaction between living organisms and the planet's physical systems. Recognizing this does not diminish the importance of the present moment. It adds depth to it. It reminds us that we are part of a system that is both vast and intricate, shaped by forces that operate on scales of time and space far beyond everyday experience. At the same time, our actions now become part of that same record. Future layers of rock and sediment will carry traces of what we have built, burned, and moved. The distribution of species in the far future will reflect the choices made in the present, just as today's patterns reflect the choices made by tectonic plates and ancient climates. The story of a planet still drifting is, in this sense, also a story about responsibility. Not in a moral or abstract way, but in a practical one. Understanding how interconnected the system is makes it easier to see how changes in one part can ripple outward. A shifting climate can affect plant communities, which influence animal populations, which in turn shape the structure of ecosystems and the services they provide. A change in ocean chemistry can alter marine food webs, affecting fisheries and the communities that depend on them. These connections mirror the ancient ones that link the breakup of a supercontinent to the rise and fall of entire groups of organisms. The difference is that now, a significant portion of the change is driven by human activity. This places the present moment in a unique position within the long history of the planet. It is a point where the slow, deep time processes of drifting land and evolving life intersect with the rapid, conscious actions of a single species. How these two threads will weave together in the future is still unfolding. From a quiet, reflective perspective, there is something both humbling and grounding in this view. The ground beneath our feet has travelled across the globe over hundreds of millions of years. The species around us are the result of countless branching paths of survival and adaptation. The climates we experience are shaped by the arrangement of land and sea that began when all the continents were one. And yet the story is not complete. The continents continue to move, the oceans continue to flow, life continues to change. The planet is still, in a very real sense, becoming. In that ongoing process, every moment is both a continuation of what came before and a starting point for what will follow. The breakup of Pangea set the stage for the world as we know it, but it did not write the final lines. Those lines are being written now in the slow slide of tectonic plates, in the shifting patterns of climate, in the migrations of species, and in the choices made by the humans who have become part of the system. A planet still drifting is a planet still telling its story. Not in sudden declarations or dramatic conclusions, but in a steady flow of change that carries the past forward into the future. One movement, one adaptation, one quiet transformation at a time.